which is used for the designing of slabs, beams, foundations like isolated, combined, raft or mat footings. So here in the help we go in the about SAFE. SAFE 2016, what the abbreviation of SAFE? It's a slab analysis by the finite element method. So first of all, I will show you how to define the material properties in the SAFE software. File, new model. First of all, the user can select the code as per his country. So here I am selecting ACI 31814, design preferences, definitely the code, etc. Here is again the code, phi tension, these are the factors for compression, for shear, minimum cover for slab, and what bar I am preferring. So all these settings is present in the design preferences. In the project information, here you can put all the information, and when you go for printing and for reporting, then all the information automatically comes on the report. Then the fourth one is the units. Currently is metric. Here is the unit system, so you can change the units into metric into FPS by just simply one click. US, all the units now in converted into FPS system, US defaults. And you can also select the units as per your requirement. For example, if I want to work into the kg centimeter, so here is the kg force and centimeter. Okay, now all the units will automatically convert into kg force into centimeter, but I am comfortable with metric system, metric default. Okay, now there is many templates already available. For example, flat slab perimeter beams, two-way slab, base mat, combined footing, single footing, ribbed slab, waffle slab, and grid only. So first of all, I will just select the blank. Now I will go in the define material properties. In the material property, these are pre-defined materials. So here I will define the material, add new material. First of all, I will define FC prime, that is a concrete strength, for example 28 megapascal. Here I will select material type, that is a concrete, and here is the specified concrete compressive strength, that is the 20 megapascal, Newton per millimeter square. 1 Newton per millimeter square is equal to 1 megapascal. Here I will put 28 megapascal. When I change the 28 megapascal, software do not automatically calculate the modulus of elasticity, so we have to put it by ourselves. For example, I will put 4700 multiply by 28 power 0.5. Basically I have put the formula 4700 under root FC prime, that is the formula for the calculation of modulus of elasticity as per ACI code. So I will hit enter. Software automatically calculate the values from the formula. So Poisson's ratio for the concrete, that is 0.2, coefficient of thermal expansion, and shear modulus software automatically calculate. So if the lightweight concrete, you can put the reduction factors, but in this example I am using the normal concrete of 28 megapascal. Okay, so that's how I have defined the concrete material. Now I will define the steel material, that is the rebar. For example, F5 for 20 megapascal. You can define 300 megapascal for 20 megapascal as per your requirement. Here I have put the for 20 megapascal. I will select the rebar, that is the reinforcement material, and the modulus of velocity, that is a 200,000 megapascal, that is a 200 GPa. That's okay. Minimum yield strength, that will be for 20 megapascal. Ultimate strength, that will be 620 megapascal or 610, that will be okay. So that's how you can define concrete and rebar material or reinforcement material in the CSI SAFE software. Now I will define the slab sections, beam properties. For example, in the slab section, here I will define add new property. For example, I am defining the slab, that is a 150 millimeter. So here is the property 150 millimeter. There is slab material. I will select the material I have defined, FC prime 28 megapascal, and that is a display color property nodes. You can put that is a 150 millimeter. Okay. Now I will define the material for the foundation. Add new material. Here I will select, for example, I am designing the footing, mat, rib slab, waffle slab, stiff drop panel slab. So now I am selecting the material footing, and now I will put the thickness 300 millimeter, that is the footing 300 millimeter. The material strength is 28 megapascal. Okay, so that's how I can define the footing properties. Now I will make another property of for mat. Add copy of this for mat, that will be, for example, 600 millimeter. Concrete property, slab material, and here I will select the mat, put the 600 millimeter. Okay. So that's how we can define the slab properties for the for our foundations, for our slabs, etc. Now I will define the beam properties. In the beam property, I will simply define a beam section of 300 by 600 millimeter. So here I will select the beam material, FC prime 28 megapascal, rebar material for 20 megapascal for longitudinal reinforcement, and for the shear or ties I will select also, but you can also define the 300 megapascal 300 megapascal grade steel for shear or ties. So here are different shape options. For example, rectangular beam, L beam, T beam, or general beam. For example, in the rectangular beam, here is a web width. For example, here is a web width at top and bottom, and what is the depth. So here is a rectangular beam. Here is I will click show properties. Software automatically calculating the cross section area, moment of inertia 2, moment of inertia 3, shear area. So what is 2 and 3? Here is a vertical. For example, in our manual calculation we use x-axis and y-axis. Here is a y-axis 2 and x-axis is 3. So moment of inertia about 2 and moment of inertia about 3. So here so that's how the software calculated the properties. So for example, if I want to define the T beam, so here the property is web width at top and bottom, that is the 300 millimeter. Depth of the whole section, that is a 600 millimeter. Flange width, for example, at top, how much is the flange width of T beam? So here I am putting, for example, 800. Here you can see now T beam is appearing here. So slab depth you can also adjust, for example that is a 150 millimeter. Okay, so that's how you can, for example, define the T-beam. So you can also select the inverted beam here just by clicking here. Similarly, you can define the L beam or general beam. General beams any shape. So I have selected the beam that is a rectangular shape. So I will click here and just the width is 300 millimeter at bottom and at top, and depth is 600 millimeter. These are the clear covers. Design property data, for example, flange dimensions in the analysis, how much flange dimension should be used in the analysis. So software automatically calculates by these options. So here is the clear cover. So that's how we can define the beam properties in CSI SAFE software. For defining of column, I will go in the define column properties. Before there is reinforcing bar sizes. So here number 6 bar, number 8, and its bar area, bar diameter. There are also different, for example US soft metric, here US customary here. So these all bars are present in 8 tabs. You can select as per your requirements. Okay. Detailing results are currently available. They will be deleted if okay. Because I have not generated any detailing results, so it will not matter because I am overriding the bar sizes. Now I will go in the define tendon properties for post tension slabs. So here is the column properties. For column properties, I will click add new. Here I will define column 300 by 300 millimeter. So here again material is FC prime 28 megapascal, display color, notes, column shape. So there are different shapes: T shape, L shape, general, circular, and rectangular. Because I have selected I want to make a column of 300 by 300 millimeter. Here I have put the values. Here include automatic rigid zone area our column to control the deformations. So I am making a connection between the slab and column so that column control the deflections. So here is a two options for drop panel and for drop capital. If I want to create a drop panel, so here is the option how much is the dimension of drop panel in the 2 direction and in the 3 direction. Here it is 1.2 meter. So here I will put it to, for example, 1400 millimeter. 1400 millimeter. So why I am changing at the start we put tentative values, for example 1000 millimeter, 1000 millimeter, and if our punching shear check is okay, so then we can optimize up and down. If the check is not okay, then we will definitely go towards the higher values of the drop panel. Further, for the slab property we can also define the drop panel thickness in the drop panel area. So for example I will go go back again in the define slab properties. Now I will again define a new property that is a drop, that is of 250 millimeter thick. So here I will put 250 millimeter, and the property of material is also same, and that is a drop. Okay, now when I will go in the define column properties, modify, here I will select my material drop. Now the drop thickness will be 250 millimeter in the drop panel area. If I want to create a further column capital, you can see in the picture what is the column capital, drop capital and the drop panel. So you can also further create a drop panel, drop capital. So that's how you can define the column in SAFE to CSI SAFE software. Okay. Now I will define the load patterns. Here is the load pattern, dead, 1, live, 0, and you can also make another, for example, earthquake. So similarly, you can define more load patterns in the SAFE software. Here is a defined load cases. In the defined load cases, for example, dead, modify. There, what are load cases? When we define the load patterns, then load cases define the property that how loads pattern should be applied to the structure. So there are 3 load case types, that is a static, model, and hyperstatic. Hyperstatic is used for post tension slabs, and model for calculation of time period, natural frequency for these purpose by eigenvectors, Newton's vector, and for our analysis and design we use the static case. So there are the 3 different options: linear, non-linear, allow uplift, non-linear crack, non-linear long-term crack. For non-linear long-term crack, we also have to provide the creep coefficient in shrinkage strain, so that we can calculate the non-linear long-term cracked behavior. So for the normal calculation, we often use the linear static. For the different cases of non-linear allow uplift, I will discuss in the next lectures. So here for live, that is again live 1 and non-linear behavior. Okay. Now I will click define load combinations. In the SAFE, we can define by manual, for example 1.4 dead. So here I will put 1.4 dead. Okay, the load combination type is, that is the strength ultimate load combination type. Okay, now I will also define a service load combination in which all things are 1 1 1 dead plus 1 live plus 1 earthquake. Again I will select in dead is 1, second live is 1, third earthquake is 1. So that's how I have made the combination. Again, there are different types of making the combinations. Here are linear addition, in valve, absolute addition, SS, range addition. SRS is basically square root of sum of squares. So these are addition types. For example, how we add the load combinations. So we normally use in our designs linear addition. So that's why I'm clicking here. So now the load combination type is service normal. Okay, so these are, that's how we can manually enter the load combinations. Now we can also add default design combination. The software can quickly add, for example, I want the ultimate load combinations as per ACI code. Okay, software automatically generate the load combination. Here you can check 1.4 that software automatically created. Okay, you can also add that's up to you. So that's all for the load combinations. Now for the defining of soil conditions, that is bedding pressure, settlement. So how we simulate the soil conditions in the software. I will go in the define soil subgrade modulus. Here is a soil defined previously, that is the previous defined function. Now I will create a new, add new property, soil boundary, soil spots. So soil spots. So what is this soil subgrade modulus? There are 4 options. Linear, it will take both as a if there is any compression or tension. that is a tension only, and that is a compression. We in our footings, all the loads are acting on the footing as in a compression sense. The footings are trying to compress the soil, so that's why we select this compression only. And here is a soil subgrade modulus. What is the difference between soil subgrade modulus and bearing pressure? Here is a soil subgrade modulus. Bearing pressure is the pressure, for example, force per area, but the soil subgrade modulus is the pressure per settlement and deformation. So here pressure is allowable bearing pressure, deformation is allowable settlement in the foundation. For example, allowable bearing pressure after the soil testing report, you get 200 kPa, and allowable settlement is 25 mm for the isolated footing. The soil subgrade modulus will be K is equal to 200 divided by 25, that is the millimeter. For the conversion into meter, I have divided by 1000. Now the answer is 8000 kilonewton per meter cube, or you can say 8000 kilo pascal per meter. So this value you will put if you have the properties of the soil 200 kPa and the settlement is 25 millimeter. So here I will put 8000 kilonewton per meter cube. Okay, soil spots, I will again modify it. It is for isolated footing. Okay, then in the design we will check three things. If our pressure under the footing is less than 200 kPa, our allowable bearing pressure, then it is okay. A deformation should be less than 25 millimeter. For punching shear, it should be less than 1. Preferable should be not more than 0.9. We will see in the next lectures. Tips: if you are failing in any check, bearing pressure, deformation, punching shear check, go towards the following change. Inputs like geometry change, length, width, and thickness of the footing, and material property. For example, if my pressure, I am failing in pressure, so I will just increase the area of the footing so that my load spread into the more wider area. So I will also discuss in the next lecture. So here it not allowable settlement for isolated footing 25 millimeter, allowable settlement for mat or raft foundations, that is a 50 millimeter. The above calculations are for isolated footing, and for raft and mat foundations I have to divide in the under with 50 millimeter. So just I will put here calculate the 200 divided by 50 divided by 1000, so bracket close, equal. So here the answer is 4000. I will just go in to property, add new property, or I can just make the copy, add copy of the previous property. Now the soil conditions is for soil spot for mat foundation. Okay, the value is 4000. Okay. So that's how you will simulate the soil conditions in SAFE software. So how we can make the footing and apply these settings, I will discuss in the next lectures. In this lecture I will discuss about the mass source. Mass source is a mass which is used in the analysis of lateral forces, in the analysis of seismic design. So for that I will go in the define mass source. Here is a mass source options. So what is mass source? Here is a formula for the base shear calculation, that is equal to V is equal to CSW. Here CS is a seismic base shear coefficient and W is a seismic weight. So for calculation of base shear, the effective seismic weight is very important, that is a mass source. So in the mass source, what parameters are included? So here I will click 12-7-2. Here is a effective seismic weight. For effective seismic weight, it includes the dead load of the structure, and the second is for live load, minimum 25% live load, and where the inclusion of storage loads adds no more than 5% the effective seismic weight. At that level, it need not to be considered, means we can ignore it. And for partition load, we have to also consider the partition load minimum 10 pound per square feet. And for if there is a machinery, heavy machinery, so for a total operating weight of the permanent equipment, that must be, for example, the lathe machine, for that the load of that machine should also be added in the effective seismic weight. And this is the for snow area, if there is a snow, that percent, and weight if in the roof, landscaping, and multiple things are used, then that also include in effective seismic weight. So how we add the effective seismic weight? Here is a dead one, means consider all the dead load, and here is a live load, that will be considered 0.25%. and if there is any super dead load, or for example the load of machine, so then we also first of all define in the load pattern machine load, and then we will put here as it 1. So consider all the load. So we are ignoring the lateral mass, and uncheck this option if you want to consider the lateral mass source in the seismic design. You have to uncheck this, and okay. So that's how you define the mass source in SAFE 2016. In this lecture, I will discuss about how to analyze, design the concrete slab with drop panels. So here I will start from the scratch file, new model. Here is a design code, that is ACI 31814. There are different codes, all are also available, you can use. So here I am using American Concrete Institute code, design preferences. Here you can put the factors, design factors, minimum cover. Okay, project information, you can put the project information, and when you put at the end of the printing report, this information automatically come on the report. Here is the unit system. There right now unit system are in metric system. I will click US default. You can also further customize the unit system from each entity, so you can control the decimal places, mean accuracy, or how much accuracy you want to see on your results, so you can increase or decrease depending upon your requirements. Okay, here I have clicked US default. Okay, here I will click grid only in this lecture. Here I will select the grid system. I will draw grid 5, maybe 7 grids in X direction and 8 grids in Y direction, and spacing for the X is 16 feet and for the Y grids are 20 feet. Okay, and these are the values I have put, so I can even edit the grid spacing between in 2 grids here. That is the X grid data A, B, C. So here is ordinate 0, 16 means cumulative values. For the spacing you have to click here. So here I am changing the value between A and B grid data is 16 feet. I am changing the value between C and D, that is again 20 feet. So similarly here I am changing the value between third and fourth, that will be 15 feet. You can see the changes are appearing here. You can also adjust the bubble size, that is 16 inch. You can change if the bubble size is looking bigger in the model or smaller. So here is a story height. Story height above is 0, story below means column height will be 12 feet. You can also adjust, for example here I am putting 13 feet. Okay, for journal, if you want have any inclined grids, you can put from journal grid data. Okay, so here is a grid appearing which is I have created. You can also make invisible this horizon which is displaying behind. Okay, now we can see the grids clearly. Now I will define the material property. Here is predefined material property 5000 psi and grade of steel is 60. So I will use just I will review, modify. Here is a 4 ksi means 4000 psi. Okay, and here is grade 60 steel. Here is a 60,000 psi. Okay, you can create new material up to your requirements. Define slab sections and new property. So here I will slab make of 8 inch. You can put in words also. Here is this type property slab that is 8 inch. So in this example I am taking the slab thickness is 8 inch. So there are different types for drop, stiff, and here is a thick plate. Thick plate that will consider the in plane and out plane moments and design the actual behavior of the slab. And for the orthotropic means if the dimensions of the slabs are different in different directions. For example, if I click here, so here you can see in local 1 direction and 2 direction, if the thicknesses are vary, so you can use the orthotropic. So our slab is prismatic throughout the plan. So here I have selected the thick plate. Okay, now I will create the drop panel that will be 12 inch drop of 12 inch. Slab property, slab material property. Here I will select drop and the thickness will be 12 inch. Basically why I am selecting 12 inch, for example if my section fails, then I will come back and increase the thickness into 13 inch, 14 inch. So whenever my design will satisfy, so that thickness will be final. So here are the tentative, for example for drop that is 12 inch and for the simple slab that is 8 inch. Okay, okay. Here I will before moving further I want to save my model. File, save as, slab with drop. Now I will define the beam properties. So I will also show how to draw the beams define. So here I am clicking at the beam property. Beam will be 12 by 15 inch. That will be beam material type, rebar material, shear rebar material, and properties nodes. Beam type, it's rectangular, so I want to take it as L beam. So here is the web width at top, that is 12 inch, web width at bottom, that is 12 inch, and the depth is 15 inch. Flange width means the flange slab depth, that is 8 inch. So here I will put 5 feet. Software automatically convert into unit system. So here now I have created the L beam. So here is a show property, means cross section area, moment of inertia, all type of things. We can also use inverted beam, but in our case that will be okay. So here are the design property data. Flange dimension from analysis property data means the value flange which is I have put it in the analysis property data software will use in the design. The second option is flange dimensions automatic from slab properties. Software put the formulas and take the flange for the flange width for the L beam automatically from the formulas. And third is user defined. You can put the flange here, the flange different values, but I will prefer take the values which I have put it in the flange width analysis property data. Here is a cover from center of the bar to the outside, so here 3 inch. Okay. Now I will define column properties, add new column. So I will define the column with draw panel. So column sizes will be 15 inch by 15 inch. There are also different types of column: rectangular, circular, L shape. You can select according to your requirement. So here I will select include automatic rigid zone area our column, so that the column will act as to control the deformations of the slab. So you should must check this option. So for drop panels, here is the option. There are two things: drop panel and column drop capital. So you can see in the picture here I am putting the drop panel dimensions in the 2 direction and in the 3 direction. 2 direction means X and Y. You can take it as that is will be 5 feet. So here I will put 5 feet. 5 feet. You can put 60 inch or software automatically convert into inches. So here I will select the property will be drop 12 inch. So that's how you can define the column properties. If there is a drop capital, so you can use this option. Otherwise for the drop panel, that option is okay. Now I will define the load patterns. In the load pattern, that will be okay. For the creation of load combination, I will definitely go in the ultimate strength design and auto load combination. You can also draw manually. Here you can see 1.4 dead according to ACI. Modify 1.2 dead plus 1.6 live. Okay. Now I will draw the slab. So here are different options for the draw slab. Here is a draw slab. Here is a draw rectangular slab. It is a mean journal slab. In this you can only draw in the rectangular. Here is a quick draw slab. Here is a quick draw area about points. So different options we will discuss in different lectures. So here I am selecting the draw slab. So for the slab I will select the 8-inch slab. So now the software is showing me the values that edge drawing type, it will be straight line, circular or arc. So you can select. So in this example our slab values, slab edges are straight line. So here I am selecting. Okay, for the last value you have to just hit enter. Software automatically draw the slab, that is a 8-inch slab. So now I will draw the columns, and for the edges I will draw the beams. So for the draw of columns, here is a quick draw beams, here is a draw column. So here I will click draw columns, and I have defined only one column. So here column width drop, and height below that is 13 feet, and height above that is 0 feet. Means above I am not taking the column, only from the slab downward 13 feet. So here I will start drawing one by one, or you can quickly draw. For example, here software automatically trim the edges. Here Okay, so you can also quickly draw by just selecting all the grids where you want to draw the uh, column column with drop panels. Here software automatically drawn. So here just I will select to deselect the draw mode. I will select delete. Okay, now I will project my slab, means make the offset of the slab 1 feet beyond the grid line. I will select the slab and go in the edit areas and expand and shrink areas. Here software asking the software asking from me the how much I want to make the offset. So I will make it 12 inch. Here software automatically here the mistake is I have the software not drawn the panel, so I will just delete these columns and go again in the draw column. Here now you can see software automatically trimmed. These are the two extra columns. Here I have deleted the extra columns. Now on the boundary I will draw the simple columns and with beams. So for simple column I will again go in the define column properties, add copy of this previous column but no drop. So here I will uncheck only the simple column 15 inch by 15 inch with no drop. So you can also put 15 by 15 inch. Okay. Okay. Now I will again draw the columns on the edges here. So basically the property is selected column with draw panel. I will click Ctrl Z and select the column with no drop here, here and here. All the columns have been drawn. Now after drawing the columns, now I will draw the beam. Here draw option, draw beams, quick draw beams. So here also both options are present. So here I will click draw beam. Here I have only defined one beam, so that's why only one beam is appearing here. So now draw beam here. You can click one by one, but here you can see software automatically make the beam for each panel. Right click, or you can click the draw click select mode. The automatically draw mode will disable. So now I have also drawn the beams, draw panel, slab. So now I will define or draw the design strips. So for the design strips I will go edit, add / edit design strips, add design strips. First of all, in the X direction I will grid direction X and the strip layers are A. Okay, so here you can see grids are defined. So now I will click edit, edit design strips Y and the name is P. What are these design strips? These design strips are used for the designing of slabs by using strip design method. So when we design, after that we will display the results by using design strip method. So that's why we are defining. Now I will in the draw the Y direction. Here you can see. So these are extra. You can delete or trim but if there are extra no need, so of software only give the results which are present on the slabs. So now you can also draw by yourself. For example, here I am deleting one grid, one design strip. Okay, now I will draw design strip. Okay, so that's a direction for the x, and that's a column strip. So the start width at right, it's left, and right width and end width at this. So you can adjust accordingly. So here I am just putting 5 feet at the start, 5 feet, 5 feet. But when software draws, software automatically determine the design strip widths. Here is the start, here is the end. I will right click, close. So that's how you can also manually draw the grids. Now I have almost drawn, load combinations are also defined. Now I will run the analysis and design. For automatic mesh, software automatically make use rectangular mesh 4 feet by 4 feet. Okay, so now I will run analysis and design. Okay, after running the analysis, you can see the finite element model. Okay, this is showing the deformed shape for that in inches. So when you move your cursor, you can see the deformation. Here is downward deformation is minus 0.06. Here is minus 0.087 inch. Here is minus 0.089. So here in the color you can also see here is very less uh, deformation. So now in the display you can also see the show of deformed shape against load combinations. For example, 1.2 that plus 1.6 live apply. Okay, so here now the deformations are more because now the dead and live both are present. So now I further move for punching shear so that my shear check is okay or not. Here the for the beams not need to calculate, but for the drop panels which are provided that are okay, all the demand versus capacity of shear is okay, so it should be less than 1. So you can optimize here. So now the drop panel that's value is 0.26. You can decrease the slab thickness to 6 inch and the drop panel maybe 10 inch. So you again run the analysis, then this value will optimize, will maybe reach near to zero point 0.8, 0.6, which is also okay. So now I will display show slab design. Here is design basis strip based. Okay, so now I will click the layer A and layer B apply. So now you can see on the whole of the slabs the strips data reinforcement data is given, top and bottom reinforcement in inch square per feet. So for example, I will take any panel. So for example, let me zoom this portion, this end grid here. So now for example, when I will move in the edge, so here is a top and bottom. You can see at the edges top area is more, bottom is reducing. Similarly in the slab, bottom area is there, no need of top. Similarly here you can see. So you can also impose the minimum, that's a requirement of the code apply. So it means the minimum reinforcement will govern because the reinforcement which is calculated against the loading that is very low. So we will provide the minimum reinforcement because minimum reinforcement is governing the criteria. Okay, now you can also see this same method. For example, in the a finite element. So here is the finite element. Okay, now for the one direction is the x direction and the two direction is the y direction. Now I will see the bottom reinforcement by finite element method. Apply, impose also minimum reinforcement. Apply. Here you can see at the columns there is no need of reinforcement, but in the center there is a need of reinforcement in the x direction. Similarly, for example, let's see in the top in the y direction. Apply. So here only at the columns top steel is needed. In the span in the mid of the beam spans, no need of reinforcement. So you can also calculate the reinforcement. For example, here is a typical uniform reinforcement. For example, number 4. Let's see that will be okay or not. For example, in the top. Apply. Okay, so there is still need of reinforcement. I am reducing the spacing. You can step down by uh, in increments. Here now you can see more. For example, in this at the draw panels, extra reinforcement is needed. So for the example, for the bottom steel, apply. Okay, in the bottom 4 inch 8 inch by 8 inch spacing is okay. For example, let's see 10 inch by 10 inch. Apply. Okay, so there is some at some points there is a need extra steel. So that's how you can design the slabs uh, in SAFE software. So say here, apply. For example, if I am saying apply, so here is the reinforcement. When I apply provide the reinforcement number 4 uh, 10 inch in the top, number 4 10 at 10 inch spacing uh, at bottom. Apply in layer A and layer B in X and Y both direction, also applying the minimum criteria. So here almost every area is covering, only just here. So here you need to provide extra steel. Close. Now there is one beautiful function, that is a detailing. In the detailing you will definitely first set the preferences, unit system, all the things. Then the detailing for the slab reinforcement, what bar area you prefer. Here is a minimum, for example maximum 4. So let's see design, just select the number 4, enable also minimum, that is definitely 0.0018 bh, which is the minimum reinforcement criteria. So prefer the bar size, definitely point number 4. The column strip middle and column strip top and middle strip top and bottom. Okay, detailing, there is also further, for example drawing sheet size, drawing format properties. After that you have set the preferences, just click run detailing. So here is the detailing. So you can detailing, you can see the detailing from here, or in the explorer window you can also see all the drawings which are generated by the software. So here is the slab views, that is the framing plan which is appearing here, and bill of quantities, rebar schedule. Okay, slab views, rebar plan, for example top rebar plan. Okay, bottom rebar plane. Similarly, section 1, section 2. Okay, what are the locations of the sections? You can see in the framing plan, section 1, section 2. So that's how you can detail, and for further study you can print these drawings and study these drawings. One thing we have not see in the results, that is a beam design. Here I will go in the uniform shape. Software automatically come in the original shape. Here I will see display, show beam forces and stresses. In that we will see the, for example, moments, shear. For example, in the load combination I will select second combination, major moment. Here you can see, because we have provided the beams at the perimeter, at the mid there is a moment, at the support there is a negative moment, positive moment, negative moment. And for example, if you want to see major shear, here is also major shear diagrams. Close. Now I will go in the display, show slab design, show beam design. In the beam design I will see the longitudinal rebars. Okay, so here is for flexure and torsion. So here I'm saying for the flexure, apply. So here what are the, for example, at top, at the mid there is no need of top reinforcement, only bottom. So when I go at this port, there is no need of bottom reinforcement, only top. So that's how you can design the beams uh, in CSI SAFE software. Close. For the beam drawings, software also created the beam drawings. For example, here is the beam framing plan, individual view. Here is a concrete section, elevation of full beam, and sections. Software also shown the sections, so you can study in details the detailing of CSI SAFE, and you can also edit by exporting into the export view in the AutoCAD DXF format, AutoCAD drawing format. Close. So what is checking software, this software CSI SAFE is checking that the AutoCAD which is installed on this laptop, is it compatible or not. So just that, after that you can export and you can edit there the drawings. So that's all for slab design with draw panels in CSI SAFE software. In CSI SAFE, we can edit the geometry of beams, columns, slabs by three ways. One way is we can by right clicking change the coordinates. Second, by changing by using reshape mode. And third one is edit move points slash lines slash areas. So here first of all I will show by coordinates. For example, if I want to change this joint location, so here I will right click geometry. Here is geometry. So here is the coordinates of this joint is 101 feet and -1 feet. So here I will change the x coordinate to 103 and change to y coordinate more down to bring at somewhere this location to 4. So here I will click OK, then OK. Now you can see software automatically change the geometry of this slab. So now I will change the geometry of second corner. For example, this left top corner, I will just click reshape mode and click the slab. You can see these blue icons are paired. So I will just pick that corner and move upward. So that's how we can change the geometry. And for example, if I want the location of, for example, of the geometry from which point to which point I want to take, for example, I will press Ctrl Z. So first of all, I will draw a reference point. These are just points for the reference. Draw point. For the point, I am making x is minus 3 feet and y is minus 3 feet. So here I will go and click at the center. So that is minus 3. So just put the upward. For the upward, I have to put positive 3. From this location, upward 3 and minus 3. So here, now that's pinning the reference point. Now I will again click reshape mode, click and pick from this point to this point. So that's how we can edit the geometry by reshape mode. Now by third method, for the edit of geometry, I will use the move command. I will click this point and go edit, move points. So in this I will just change the y, I will not change the x coordinate. So here I will put -4 only, so that the point comes directly downward. Okay, so here you can see points comes directly downward. So that's how you can edit the geometry. Now for example, I will draw the wall. I will click draw wall. So here is by default wall is present. So the below height is 13 feet in our model. For example, I will draw a wall from this point to this point. Press escape key. I will come back from the draw mode 3D. Here is a wall. So when I will click reshape mode and click the wall, so for the wall I can move upward and downward and left and right, because that option is appearing. So here for example, if I want to move downward, okay, that is the option. If I want to move horizontal, I have to click the horizontal reshaping icon, for example here, and make it horizontal. So that is becoming the inclined slab. So that's how you can edit the geometry in CSI SAFE for the walls. Now further one point, for example, when we click the reshape mode, I am pressing escape. Here it is reshape mode. Here you can see in the left side only one pylon is appearing, one point here, one point here, and this point is for the offset movement. For example here in the movement of the offset, but you can see only a one line is there. So make the portions of these lines. Control Z. You have to just click the edge of the slab, click, escape, click here, one area, one head selected. So I will go edit slab, edit areas, split area edges. So now I want to split this edge into not two, maybe into 5. 1 2 3, 3 portions are enough. Okay, now when I will click reshape mode, here you can see 3 1 2 3 3 portions have been created by the CSI SAFE software. Now I can independently move, for example this point here and here. So that's all for the edit command. Thanks. How to import the grid system in CSI SAFE software, or how to import the architectural plan in the CSI SAFE software and draw the slab, columns, etc. So here I will close my files. Okay, now I will go in the CSI SAFE software, file, new model, blank. Okay, now file, import dxf/dwg architecture plan. Here is the architecture plan. Here is a grid only. I am selecting the architecture plan. Okay, please check that the unit system. Okay, in the drawing, the unit system of the drawing was in system, so here is also in system. Okay. Okay, now you will see all the architectural plan in the CSI SAFE window. So here you can draw the slabs, beams, columns, etc. Quickly. For example, for to draw the column in the define column properties, add new column. Here is a default column is column 12 by 24, but our column size is 18 inches by 18 inches. Okay. Okay, software automatically pick the column and draw the column. For example, here I am zooming the window. Okay, now I will click draw column. As I my column my cursor go to the column, so please here if the arc view appear, then click convert to column. Software automatically make the column. Similarly, here convert to column. Here convert to column. Here convert to column. Software converting the columns. Now how I will draw the slab, just even the curved slab, just I will go in the slab. For example, you can see our default column size was at 12 by 24, but our CAD column was 18 inches by 18 inches. Here you can see column properties. Software automatically make the second column that is of 18 inches by 18 inches. So here click OK. Click OK. Now in the define slab, for example, slab properties, if there is already slab 1 and stiff slab is present, now I will create a new slab of 6 inch. Okay, 6. Okay. Okay, now I will draw slab. Here I will just go near the edge and right click here arch area, just click add area, safe area. So here you can see the slab is appearing. I will right click, I can check the slab is 6 inches because here is slab in 6 inches. So that's how you can draw all the elements in the CSI SAFE software. Hi, in this video we will learn how to analyze, design and detail the slab in CSI SAFE software. So from starting new model, now I am doing the design preferences. In the design preferences you can change the values like clear cover and what bar you prefer in the design of slab. So here I am changing some values. So you can also provide slab minimum reinforcement 2-way or 1-way. Okay, now I will click the project information. In the project information you can add the values whichever you want to like. For example, you are doing some project, then you can add the values of that project, like who is the client and who is designing the project, and what is the number of this project, and you can assign any values in that. So here you can change the units, FPS system, metric system, etc. So let's start with the grid system. So in the X direction I will provide 4 grids, and in the y 3, and in the x direction spacing is 6 meter, and in the y direction the grid spacing is 4 meter. Then I click OK. You are saying the grids which I have created. Now I am going to modify as desired, as I want. So here is the spacing showing between A, B, C, D, 6 meter, 6 meter. I am changing the spacing between different slab, between different grids according to my need. So here, here you can also change the story height for the column. So I put 4 meter and click OK. So you can see the grid system generated according to our needs. So I am removing the smaller grids which is appearing ABCD grid behind. So I removed that. Now I am going to define the material. First of all, concrete material of strength 28 megapascal. So in the materials type I will select concrete. So here I put 28 megapascal, and you can also change the modulus of elasticity according to this strength. So it depends upon you. And new material, and now for the rebar or reinforcement, so I will select for 20 megapascal rebar. So here I put the yield strength for 20 megapascal, and the ultimate strength is 630 megapascal. So that's how I define the material property for the rebar. Now I click OK. So here I have defined successfully concrete and reinforcement material. Now I am going to define the slab property. So here I am defining the slab of 150 millimeter, and the concrete slab material is concrete 28 megapascal, and the thickness of the slab is 150 millimeter. You can also define the material for different slabs like waffle, ribbed, and etc. So now I am going to define the beam material. In this beam there are different options are also present, like you can also define not just rectangular beam, also L-shaped beam, T-shaped beam, or any general shape you can also define in this beam section. So I am going to basically define a beam of 300 by 600 millimeter section. Concrete material is 28 megapascal. Rebar material for longitudinal bar for 20 megapascal. For shear is also for 20 megapascal. So here I am showing just little bit how can you define the L or T shape beams for general beam. So here for L shape beam, so in the flange width you can provide the flange width, like here I have defined for the L shape beam. For inverted beam you can just by clicking on the check option, then you can see the inverted beam. You can also change the clear cover. So basically I am defining the rectangular cross section beam 300 by 600. So top width and bottom width at the top section and at the bottom of the section, and the height of the section. So that's for the beam. Now I am going to define the column. So I will define the column of 300 by 300 millimeter cross section. So I put the name of the column 300 by 300, material concrete, and column shape. Maybe you can also define different shapes of columns, L shape, T shape, rectangular, circular. I will define here rectangular or square shape column by providing 300 millimeter width, 300 millimeter height. Okay. In the load pattern I will just define the basic load patterns, then I will go the load combinations. I will define the load combinations for the two load patterns, dead and live. So that will be 1.4 dead, 1.6 live. I am basically designing the slab according to strength design or LRFD. So I will select the strength design combination. Okay. Now I have successfully defined the property and load combinations, etc. Now I am going to draw the slabs here by quick. I will try different options for the drawing of slab. Like here, you can, by clicking the points, you can also draw the slab. So here you would first press the one corner of the one corner and then click to the right bottom. So similarly, I will pick one point and now click on the left top corner. So here you can also by define the slab by clicking points one by one and at the end closed. So here I have defined the slab with different ways. Now I am going to provide the beams at all the corners of the slabs. So you can also provide draw these beams at an offsets. Here I am defining the slab, defining the beam, sorry. Okay. The highlights of the beams are not so much because the beams are present under this slab, so we can check that thing in the 3D model. So now I am going to assign the columns at each intersection. So just by clicking the column at the joints. Here you can see I have successfully defined the slabs, beams and columns. Now I am saving the model. Six panel slab design using CSI SAFE software. Okay. After doing all things, now I will run the design analysis. Before running the design analysis, you can check the design preferences like minimum cover of slab, minimum cover of beams, etc. So here are the just preferences, but you can also do at any design step. So design combinations are these two which I have defined in the design combinations. So here I am going to do the meshing for the slabs. So for the each mesh area I have provided 0.5 meter. So now I am going to run an analysis and design. So here we can, sorry I forgot to assign the loads on the slab. So I'll go in the by selecting the slabs. I have selected all these 6 slabs and now I am going in the assign load data surface loads. I will define the first of all dead load of 1 kilonewton per meter square. Okay, and then by selecting all the slabs which I have selected previously, I will again assign the live load of 3 kilonewton per meter square. 2.5 kilonewton per meter square. Here you can check by clicking on any slab, by right clicking on any slab, the loads dead and live that is present on that slab. Now I am running the analysis and design. Here you can see the deformation shape of dead load. I will check the deformation behavior against the load combinations. So here I am checking against the 1.2 dead plus 1.6 live. So here are the deformations like 0.5, 2 point something millimeter. Now I am checking the reactions. Apply here in the tabular form, and here are the in the arrows form the reactions at the spots. You can also change the location by dragging the tabular form on any side. Like I have clicked the reactions at joint 16. So now I'm checking the reactions for the load combination 1.4 dead. In the show beam stresses, you can check the moment 3 and shear 2. Here I have clicked the major moment. Okay, you can also, by clicking the values, you can also display the values of the moments here are the major shears. Okay, display. Now I'm going, okay, display. Now I'm going to check the stresses and the forces in the slabs, like M11 in the x direction, M22 in the 2 direction. Basically these are the checking way of by FEM, but you can also check the moments and shears by stream method, which is a good method, is a more easy way of expressing the moments and shears in the slabs. So that's why I will go to define the strips in the slabs. Add design strips. First of all, I will define the strips in the x direction. Here you can see. Now I am going to define the strips in the y direction. With strip layer name B. Okay, so here you can see the strips, and basically in each slab one strip is running at the spots and one strip at the middle. So the spot strip is called column strip and the middle strip is called middle strip. So here I have deleted the one strip. I can also draw the design strip by manually, not by just automatically. Okay, now after defining the strips, I am again running the analysis and design. So I'll again go back to check the simplified form of movements and shear in these labs. So wherever I have defined the strips, at that point only I can see the movements and shear. So the main locations are the spot and the middle, so I can check in each slab. Here, wow, that's looking very good. So this is for the layer A, for layer B in the y direction. So apply. Wow, in this lab at each location, for example at the spot and at the middle. Now I will show you how to check the reinforcement in this lab. First of all, by finite element method. So in the top, in the one direction, means in the x direction, top reinforcement, like you can see, a top reinforcement will be at the spot, and at the mid that will be minimum. So you can check at the spot the reinforcement is more. Now in the bottom I am going to apply. So here you can check at the bottom in the x direction, or you can say in the one direction, is the reinforcement. So now in top reinforcement in the two direction and the bottom reinforcement in the two direction. So that's how we distribute the reinforcement. For the strip based method, in the layer A, top and bottom reinforcement, that's you can see by dragging the your arrow on the strips. Here you can see the top and bottom reinforcements on the strips. Here you can see clearly at the middle of the slab there is bottom reinforcement, and at the spot there is a negative reinforcement. Apply. So these are the reinforcement required in this slab due to applied loads. Here you can check in the both directions, x and y. So here I am providing the reinforcement to neutralize the applied required reinforcement. For example, in the top and in the bottom direction. Here I have provided 16 number bar at the spacing of 300 by 300. I am changing here, apply. So still this is much more reinforcement, so now I am increasing the spacing, apply. Still satisfying the results. It means 12 number 350 is okay. Here when I have provided the number 10 at the rate of 350 spacing, so that is load reinforcement, so I have increased the number of the area of bar for number 12, so that is satisfying. See, we have neutralized the applied required reinforcement with the provided reinforcement. Now this is the one way. Now I will show in the detailing. So the software automatically detail the whole required reinforcement. So here are the detailing preferences, you can check as you wish. So here I am just reviewing the preferences, but you can change your own desires. Here general display settings and section in each direction I can put 2, so I can check see the sections in each direction too. So here are I am providing minimum reinforcement in each direction 0.0018 BH, which is required by the ACI code. So here I am giving the just preferences, like smallest bar dia should be used 10 millimeter and the largest bar dia 25 millimeter, and the preferred rebar sizes in the column strip and the bottom strip, and in the middle strip all things you can play with. So these are the colors for the size of the drawing. So here you can check the drawing sheet setup, A1, A2, A3, whatsoever you size you like. Okay, so after checking the preferences I will click run detailing. Here you can see the two sections appearing in the each direction. In the x direction 2 sections, and in the y direction 2 sections. These are the sheets, but for the more clear view of this slab detailing, so here you can say the slab 1, clicking individual slabs. Here in the top reinforcement showing and the bottom, so all reinforcement showing in this plan. So in the top rebar plan only top rebars will be shown in the x and in the y direction. So here you can see for example in this 1.5 meter width, 3 meter width, 8 number 12, 7 number 12, you can check the 7 number. In this portion 7 number of bars required of 12 millimeter dia. So here there are two reinforcements, 3 number 12, one is curtail and one is integrated through the spots. So here you can see the bar plans top and bottom, top are showing with the dotted and the solid bars are showing the bottom bars. So for the top rebar, so that's looking good. Bottom all bars, so definitely. So the sections, you can also check the sections. For example, here the notations you can change as you want. Now the section 3, here is a good thing, reinforcement profile. In the reinforcement profile, it shows that how much area is required and how much areas you have provided. Here is showing provided 134.3%. I have to provide almost equal, so I have provided much more than the required, so that's why it's showing that our 272%, 12%, 5%, so whatsoever, in different locations. Like in the profile B layer, here it's showing 12.2%, that's good. So and here you can see 20.3%, so that's almost okay, not a big issue. So similarly you can also check the details in this, in the beams, in the CSI SAFE software. So for the detailing, for the bars, names, etc., you can check in the journal notes, documentations of the CSI Safe software. So that's all. Thank you. Allah Hafiz. How to analyze, design, and detail isolated footing in SAFE software. Here I will start the new model file, new model. Here is the design code. Whatever is your country, you can select the design code. It's Italian, Canadian, Eurocode, IS, Indian Standard, or American Concrete Institute. Here I am selecting the latest code. Here is the design preferences. You can select preferences like what is the a design factor for tension control or compression control for shear. It is based on code, so I recommend please do not change these codes, these factors. Here is a minimum cover, so here is a 0.75 inch, so that will be 20 millimeter minimum cover for beams, that is for post tension. So here I'm clicking OK. And second, project information, you can put here client name, for example David, project number, project name, for example training, and similarly you can put, for example, project number. All these things you can put here in the information. So what is the benefit? Basically, when you go for the creating a report, so software automatically pick this information. Okay. And the last one is the unit system. So which unit system you want to work? Here is both unit system, US default and means FPS system, and second is metric system, means kilonewton meter system. And here is a consistent, you can select any unit system, kg whatsoever, kg millimeter, kg millimeter, kg centimeter. So that's how you can pick the unit system. So here in this example I will pick the metric defaults kilonewton meter system. I will click OK. And here is the initial templates. You can either start the work from these templates like single coating. Software automatically take the slab thickness. Here you can change and all the things software automatically pick. Here the combined footing. So I am start from the base level. So here I will draw all the things. I am clicking blank. Okay. After clicking blank, I will go in the define properties material. Here I will define new material, for example for concrete 24 megapascal. Okay, and here material type you select concrete, and this property window will appear. Here is the unit volume, unit weight of the concrete, that will be remain constant. Modulus of elasticity, Poisson's ratio, coefficient of thermal expansion, shear modulus. Here is a specified concrete compressive strength, that is at 20 megapascal. 1 Newton per millimeter square is equal to 1 megapascal. Here I will put 24 megapascal, and here I will put the formula. Then software automatically calculate the modulus of elasticity. equal 4700 multiplied by 24 power 0.5. That is the formula 4700 square root of 24. That is a SI formula. For FPS system you have to do 57,000 under root FC prime. Here I will hit OK. Software automatically calculate the modulus of elasticity. So Poisson's ratio, that will be constant, remain same. Coefficient thermal expansion, that will also remain constant. Shear modulus, software automatically calculate. I will hit OK. And here is a predefined steel, so I will also define the steel means reinforcement, that will be 420 megapascal. Here I will select rebar. Here is the unit volume, that will not change. Here is the modulus of elasticity. You can enter 200,000, 200 GPa, gigapascal. Here the minimum yield strength, here I will put 420 megapascal, and ultimate strength 620 megapascal for 420 megapascal grade 60 steel. Okay. Now I will define the slab property. Here I will define two properties for slab and for center column. Here I will define the footing with 300 millimeter thickness, and here I will click the slab material property. That will be concrete 24 megapascal. That will be thick plate, means all the plate will be act as a to take the bending moment, shear, all the things. This will behave like a slab. Here is a orthotropic, means if the slab have different thicknesses in different directions. For example, in x direction, what is the thickness of the slab, another direction, what is the thickness of slab. So in our case, the same thickness is for the whole footing, so I am not changing, going to orthotropic. So here I will hit OK. Now I will define another property for column. Add copy of this. Here I will define stiff column. Okay. The column property will also be concrete 24 megapascal. Here I will select stiff. Its thickness will be also 300 millimeter. Okay. Now I will define the soil subgrade modulus. Soil subgrade modulus is basically the behavior of footing, and for example in real situations, under the footing there is soil, and soil may have major two properties. One is the bearing pressure, allowable bearing pressure, and second is the allowable settlement. For isolated footing, there is a allowable settlement that will be 1 inch, means 25 millimeter, and for the allowable bearing capacity, that will become from the geotechnical report. Modify. Here I will click soil, and its bearing capacity and 100/25. That is just for my remembering purpose. You can put any name. And here is the soil subgrade modulus. Here I will put equal 100 divided by 25 divided by 1000. Here basically what I did, I divided the, for example, my allowable bearing capacity is 100, 200. For example, in this example I'll take the bearing capacity 200, allowable bearing capacity, that is a 200 kPa, and the allowable settlement is 25. I am dividing the bearing pressure with the settlement. Here you can see. Here I will hit OK. Software automatically calculated to 8000 kilonewton per meter cube. And here is a for condition: none linear tension. For tension, our for example, if the column is pulling, in pulling situation, then we select the tension only. But in our case, the load from slabs, beams, and beams come onto the footing, and the footing is in the compression sense, so that's why we select the compression only. So here is about soil subgrade modulus. Soil subgrade modulus is the pressure divided by deformation. It is a basically spring constant. So here pressure is the allowable bedding pressure, deformation is the allowable settlement. For example, our bedding pressure is 200 kPa and the allowable settlement is 25 millimeter. So the soil subgrade modulus will be 200 divided by 25. 25 divided by 1000 is because I am converting into meter. 25 millimeter into meter. So that's why the answer is 8000 kPa. Here is a we will check the bedding pressure. If the pressure under the footing is less than 200 kPa allowable, it's okay. Deformation means settlement is less than 25 millimeter, that is also okay. If the shear, applied shear divided by shear capacity, if it is less than 1, so that is also okay. Preferably that should be less than 0.9, but if it is less than 1, so that is okay. If anything is going to failure, then we will change the dimensions, thickness, or all the things. That's how I have defined the soil subgrade modulus with 200 kPa divided by 25 millimeter allowable deformation. Here I have put it 8000. You can see here I have calculated 8000 kilonewton per meter cube. Okay. Okay. Now I will go in these. There are different options for the draw mode. Before drawing, I will draw the grid. Draw. Edit grid data, add and modify grid. Here is the global grid system. Okay. I will modify. I will click spacing. Here I will add 1, 2. The thickness between the A and 1 and 2 is 3. So here I will draw another grid A, B. The distance between them may be 5 meter. Okay. Now I will hit OK. Okay. For isolated footing, this much grid is okay. I will draw the footing here or here, whatsoever, wherever I want. So here I will click draw. There are different options. Draw slab. For draw slab, I will click here. I will click first point, second point, third point, fourth point, and fifth point. This is one way of drawing slab or footing. So that is the option draw rectangular slab. For drawing rectangular slab, I will draw. That's how I will draw the rectangular slab. Here is a quick draw slab. For quick drawing of slab, I will just click between the grid system. Software automatically draw the slab. Control Z. But for isolated footing, I will prefer quick draw around the points. Okay, I will select the footing type, matlab slab type, that will be footing 300 millimeter, and dimension of the footing will be 2.5 meter, 2.5 meter each side, x dimension and y dimension. I will just click at the grid location. Software automatically make the footing. Here I have just click the around the point, so that's why around the point. Escape. Now I will again click the quick draw around the point, and now I will select stiff column. Our column size is 300 millimeter by 300 millimeter. So for which column you are making the isolated footing, draw that column. So here I will put 300 millimeter. Software automatically convert into 0.3 meter. 300 millimeter. Software automatically converted into 0.3 meter. I will just click at the center. Here is a simulation or actual condition, that is a footing, that is a column. So now I will just select the slab and go to assign sport data soil properties. Here the property I have defined, I will apply. Okay. So under that you can see the soil conditions have been defined. In 3D you can see here that is a sport condition. For the applying of loads, I will click at the center, and for that first of all I have to draw the point, because for example when I click at the center, you see here one area forward is selected, now the center point is clicking. For the clicking of center point, I will go in the draw points, Here is the 0 0. Okay, now you can see the point have been drawn. I will deselect. Now if I go in the center and just click, here you can see one point selected. Now I will go in the assign, load data, point loads. Here I will assign the loads to the footing, live load. For example, the axial load, that will be downward gravity load in the -z direction. X is this direction, Y is this direction, Z is upward direction. This is -z, means downward load. So here I will apply 150 kilonewton. Mx will be 33 kilonewton meter, My will be 50 kilonewton meter. And here is a you have to must provide this x dimension and y dimension for point loads. What is that? That will be size of your column. So here your size of column is 300 millimeter. So I will put here 300. And here is the three options: add to existing load, replace existing load, delete existing load. If I want to delete the existing load, I will click here and come here, delete, click, select the delete existing load and click OK. Software delete all the loads from this point. Second is replace existing point. Matlab if any load is previously present, then software replace the loads with this. Add to existing loads, for example, if I have applied the loads and I want to increase, I will just come here, put the loads and add. Software automatically add into these loads. So here I will select replace, because even this both options, first time this first option work in the same way because no loads is present previously. So okay, here you can see the loads have been applied. For seeing the values, you click ready. In this you can see here 150 downward, that will be single arrow, and double arrow show the movements: 33 kilonewton meter, 50 kilonewton meter. Okay, now I will define the load patterns. Define load pattern, that is the default dead one, live one. That is always one. Self weight multiplier means software automatically take the self weight of the footing. Okay, live load, that is I have applied. Okay, now I will define the load combination. For load combination, I will click at default design combination and click the ultimate. Okay, software created the two ultimate conditions: 1.4 dead and 1.2 dead plus 1.6 live. Okay, that is according to ACI. And one combination I will create for the service load. Dead plus live. Here I will put dead 1, live 1. Okay, that will be service normal condition, because I will check two checks against service loads and one check against ultimate conditions. Two check, that will be bearing capacity and allowable settlement, I will check against the service loads, and one check punching shear, that will be against ultimate conditions. Now I have defined all the things. Before first of all I will save the model. For saving the model, ISO dated footing design. Okay, I will click save. Here is the model name. Now I will define the stirrups, means design stirrups. So I will go edit, add design strips. Why we need the design strips? Basically, software uh, calculate the forces for the strip based method on these lines. This is for X. Now I will go for the Y direction, edit, add design strips in the Y direction, B. Okay, so here software created the design strips up till here. I have to move at the end. For that I will just click the reshape command and click here. From here I will take at the end. Similarly I will take this stirrup and move it to end, so that software calculate the moments at the whole footing slab. Okay, Now I have defined the grid system, load combinations, loads, all the things. Now I will click run analysis and design. Here, after running the analysis, default displacements are against that. So here are the displacement. Downward displacement is maximum minus 88 millimeter. I will go in the display, show deform shape against service load combination, combo dead plus live, apply. Now I see what is the maximum deformation. Maximum deformation is minus 6.9 downward. So downward maximum deformation allowable is 25 millimeter. So it's our deformation check is okay. Now I will go in the display, show reaction forces. I will click again in the service load combination and click soil pressure, apply. Okay, now I will come check what is the maximum minimum, and the bigger value is 55 kilonewton per meter square. Our allowable bearing pressure is 200 kPa in kilopascal. So our loading is under control, means the pressure from the above loads is less than the allowable, so it means okay, this is the pressure generated by the loads. Our allowable is 200 kPa, it means it's okay. Now I will check third check, that will be punching shear design check. Here, that is also okay, that is less than 1. For details of punching shear check, you will just right click at the uh, punching shear value. Here the software gives you detailed design, what is the unbalanced moments, what is the maximum shear capacity of the footing, what is the applied shear stress. So here is the ratio punching shear, so that is a less than 1, it means our check is okay. Okay, punching shear check is okay. Now we'll see the movement, what are the movements, what are the shear in the stirrups. Display, show strip forces, that is a very good thing. Now we will check all the things against the ultimate condition, that is a 1.2 dead plus 1.6 live, apply. In this direction, layer A, what is the maximum moment, that is a 80 kilonewton meter, and for the y direction, here that is a 1.16 kilonewton meter, that is here side 50, so maximum moment is 80 kilonewton meter. So I will click close. Okay, now I will run the detailing. Here the detailing, that is basically grid spacing 5 meter 3 meter. Here is the footing, so here I will click footing layout plan, that is a footing table. Here is the footing table, that is a footing F1, 1 number, its x dimension, y dimension 2.5 meter, 2.5 meter, thickness of the footing, that is a 0.3 meter. How many bars are required, you can see here. So just it's giving the total number of bars, that is a 7 number 14 in the in this direction, matlab x direction, and in the y direction that will be 6 number 12 bars. Here is the bill of quantity. Okay, so now for the detail reinforcement, I will go in the display, show slab design. Okay, when I will click, here is the two options, strip base or finite element method. First of all, I will click strip base because I have defined the strips here, and I will see the reinforcement in the layer A, apply. So when I move the cursor, above the strip you can see top and bottom reinforcement. Here is at bottom more reinforcement requirement, at top negligible. Similarly, if I impose the minimum criteria, means minimum reinforcement criteria, apply. So you can see the minimum reinforcement criteria will govern this design. Okay, similarly for layer B you can see in this y direction. So now how many reinforcement is required at what spacing you can also check. Here typical So now I am selecting, for example, number 12 bar. Add this spacing, for example, 250 millimeter at the top and bottom. Apply. So it means higher reinforcement is required. I am reducing the distance, for example, 150 millimeter. Apply. You can see 150 millimeter is okay in both the directions. So if I make it 200, will it be okay? Let's see. Apply. So it means number 12 at the 200 spacing in both directions is also satisfied. Same you can also check by the second method, that will be finite element method. Apply. You can see the reinforcement, for example 467 millimeter square per meter here. In the bottom X direction you can see all the results. Similarly, y direction, top 2 direction 2, that is the local axis. For the slabs, local axis 1 is X direction, 2 is the y direction, and 3 is in the z direction. Similarly for bottom reinforcement. Okay, so again you can also typical justify that will it be okay 200 millimeter. Apply. Okay, so you can see in the FEM method he is saying some more reinforcement is also required, just like to 35 or 36 millimeter scale. So I am just reducing it to 175. So only I am checking the bottom, so I need to just revise 175. So you can check for the top. Apply. So it means some more reinforcement is also required, so I am reducing it to 150. Apply. Now it's justified. So for bottom in the one direction, that is also so satisfied at this. So let's see for the top. Okay, for top that will be I think 200 is also justified. Apply. So 200 for the top spacing, and for bottom spacing that is will be 150 millimeter. So that's how you see the reinforcement design in the CSI SAFE software. So now we have seen all the things: how to draw the isolated footing, how to check the allowable bearing pressure, allowable settlement, and punching shear design. Then we have seen the design reinforcement, how to justify, and how to detail the reinforcement. For more precise detailing, you can also set the preferences for the detailing. For example, what bars you need for the detailing. So all these things you can justify in this isolated footing detailing option. So that's all for isolated footing design. Thank you. RAM connection is a software which is used for the design of base plate, beam column connection. Almost all type of connections can be designed in the RAM connection. In this lecture, I will discuss about how to design a base plate in RAM connection software. So here is example: design a hinged base plate for a W360-305. W360 means that is in SI system. In FPS system, in inch foot system, that is a W12 into 305. 305 is a unit plate of unit length. Column having a total factor load of 5000 kilonewton. Use A36 steel and concrete of 3000 psi compressive strength. So now I will go in this. That's the previous model. Open, close. I will start from scratch file, from new file. Here there is a joint type, that is a column base. So all different types of connections you can study here, the connection types. Here I am in this CB column base. If there is a brace on the right side or left side, you can select, but that's a simple hinge base plate, so no brace in the left or right. The type of the section, that's our section is prismatic, means throughout from bottom to top is same. That's the opposite connection, tapered connections. So our connection is our section is prismatic, and section is W12 into 305. Okay, you can select according to your requirement, W section, tube section. So all other different types of section is also present, HP section. Okay, and the material is A36 steel. Okay, there is also other options, other materials are present, you can select according to your requirements. Okay, okay, so here is a column. Now I will define the load patterns. Here only the live load self weight is not considered. It basically in 5000 self weight, live load, all loads are considered. It's a total factored load. So I will just select add. Here is a dead load type. I will click it to live load, and description, that is a live load, yeah, or total factored load, type is live load here. Okay, and you can also when you go edit in the loads, you can define the loads. First of all, make sure the unit system, what unit system are you using, that's our SI. Okay, in SI lengths are in meter, and axial loads and shears are in kilonewton. Okay, now I will go edit. Here is the loads option. Here I will assign a load. Here is the axial 1 axis, that is a 2 axis, and that is a 3 axis. Just like in XY axis, that is X, Y, and third one is Z. In the axial upward direction is positive, and the for application of 5000 load downward, I will write minus 5000. Okay, and for the movement M22 major movement about the major axis, about the minor axis, you can see and you can understand the movement notations. Okay, the load have been assigned. Load assigned concrete material is 3000 psi. Here is the materials for the RC. Here I can check what is the strength of this concrete. Here is a edit option. Here is a type reinforced concrete, and ultimate concrete strength is 3000 psi. Okay, I will select OK. C340, and here is a connection types, multiple connections you can study, bolts, welds, anchors, all types. For example, what type of weld, that is a weld strength 70 ksi, 60 ksi. You can select according to your requirement. Not is given in this example, so we'll take it as default. And here is the anchor sizes, 1/4 inch, half inch, 1 inch, and different sizes of like anchors are present. So now I will go in the design. In the design, I have to select the code, that which code I want to follow. So here is a different codes. You can select according to your requirements. So you can also follow ASD, LRFD. So I am following the LRFD method, and here's a total factor load, live load only 5000. Here I will assign the now connection type. What type of connection type is? Here is a basic connection type, so I will go in the base plate connections. Here is a smart pin base plate, matlab for the hinge connection, that's the option. For fixed connection, and there are also other options you can study. Here I am clicking a smart pin base plate. When I click, shear and moment connection pin base plate was assigned to join 1, close. It will take some time and then show the joint. Okay, Here you can see. Now after we have assigned all the things, steel material, concrete material, section. Now we will run the design and optimize the section. Here is edit. When we will go, our software automatically design the data, and here you can study all the things. Analysis load, that is a 5000. Analysis type, major axis, both axes you can select, but our load is axial, so it doesn't matter. Uniform pressure and steel design code 2010 LRFD for the concrete, ACI 31808. And here is the optimization area. We have put the loads, the software automatically optimize. The maximum thickness we have provided, that is 76.2, minimum thickness 6.35, and the increment is here. Similarly for base plate size, maximum distance. So these are the things software automatically optimize. Okay, then the minimum effective embedment length for the for our bolts, that is a 12-inch 304.8 millimeter. Our section type is prismatic. Here is our section material. For the base plate, if we want to for example, here I will click the 3D model. If we want to provide the stiffeners, so we can provide the stiffener plates. It's up to your requirement, but in our problem that's not present. And for example, if you want to not present this column as a center, maybe it's a eccentric footing, so you can select up to your requirement, lower left. So similarly, so in this problem that will be centered, so no option is present. So here is the thickness material, here is a weld size, that is a 5 means 5 by 16 inch. So that's a spot, means pedestal, that is the dimensions. You can also in the DXF file more clearly see that is a 2.44 meter. Here is a 2.44 meter. LX, LY you can change up to your requirements, or you can optimize. If your design value is less than 1, then your design is okay. For example, here I am changing something that's 1. Here is you can see the values change, means error. So I will just optimize so that it will not go in the failure. That is 1500. Okay, and the 1500. Okay, I am changing, reduces the size of the pad, but our design is still okay. So here is a top view, lateral view, front view, anchor detailing section. So the bolt detailing is also given. Here is our material type, that will be C40. Okay, we can also click optimize. Software automatically optimize after changing. When we click the optimize, the software automatically optimize the value. Here is the anchor position. So for example, if we want the rows per, for example 2, you can increase the number of bolts depending upon your requirement. So for this example, this will be okay. I am not playing with that, you can study. So here is the options. So software after automatically optimized. Now these are the base plate sizes, and these are the footing pad size. For the detailed results, you can click results. Software will tell all the detail analysis results. What are the sizes of base plate, concrete base, column, all types of things. And there is a one beautiful thing, that is the formulas, that is the FEM finite element method models. You can also see that this is the same area, means all the area is in compression. And here is the results. So the beautiful thing is that, for example, you want to see the formula how the software is calculated the following things. Here you can select the view formula. When you will click, software also show you the formulas how the software calculated. So here you can see these are the checks, ratios that should be less than 1. So that's how we can design the base plate in RAM connections. Thank you. Have a nice day. In this video, I will talk about how to design a base plate with axial load, with moments, moment mx, moment my, moment in major axis and minor axis. So here I will start from the base, add new model. Here there are different type of connections. I am designing column base, and description you can put base plate design. Okay, if I have clicked, then randomly clicked, so you can go back in the edit. Here I came back in the same position, and if there is any left brace and right brace is present, then you can select, but in this base plate design, no. So here prismatic section, you can select W, any section. For example, here I am selecting W 16, or maybe W 16 100. Okay, and the material type you can also select the material. So here I am selecting A36 steel, 250 megapascal steel. Okay, so here are the material property and the section. Now I will go in the for example, loading condition, what types of loads are present. So here already dead load is defined. Now I will define another load. Here add a load case. Now you can also create snow load, wind load, earthquake load, XY. Okay, live load, its type, it's live. Okay, I'm clicking OK. Combination software automatically will create. I will discuss in the process of designing base plate. Okay, so here is a generate. When you will click generate, you can select how load combination will be generated. Here is different ASC 710 ASD. Here I will select ASC, American Society of Civil Engineering 710 LRFD factor load combination design. Okay, I will click generate. Software will generate the load combination: 1.4 dead load combination, 1.2 dead load plus 1.6 live load combination. Okay, 2 load combination have been generated. Okay, you can go back and check. Yes, here software automatically created the 2 load combination, D1, D2, 2 load combinations. Okay, for the applying of loads, you can go in the edit. Here is the loads. So what types of loads you can see, the notations, all things. For example, axial load, lateral load in 2 direction, in 3 direction, just like in normal calculation we do in our classes, that the x and y. So here that is 2 and 3 axis, that is 2 is the major axis, 3. So for example here shear to, for example, M22. What is M22? Bending moment about minor axis. So 2 is a minor axis, 3 is a major axis about minor axis. So M33 bending moment about major axis, bending moment about 3 axis. Okay, minor is 2 and major is 3. Okay, so here I will apply the loads. For example, so first of all I have to make sure what unit system I am following. Here is the unit system SI. Units configuration SI, you can select. The load will be applied in kilonewton, moment will be in kilonewton meter, section will be in millimeter. Okay, so now I will go again in the loads. I will apply the dead load, maybe super dead load, that will be 50 kilonewton, live load maybe 100, and the moment I am applying that will be 35 in the M33, and M22 maybe you can select 50. So no need for in the dead load. I am deleting. I am providing in the live load, and you can select 40. So here you have applied the load patterns. Dead load, that is only axial 50 kilonewton, and live load, that is 100 kilonewton, and moment are 40 in M33 and M22. Software automatically put into the load combinations and calculate the values. I will also show how software calculated. Okay, so that's how you have applied the loading conditions. Now I will apply the boundary conditions like support condition. So further database sections, materials, connections, for example, all the database is present, materials you can select according to your type, connections, database, all type of connections, base plate. So here is a base plate connection types, bolts, welds, anchors you can study. So here I am going in the design. In the design I will here is the load ISC 10 for the steel design code. So I will assign base plate connection. So our base plate action is biaxial. Basically both moments are present, smart fixed biaxial base plate. So it will take some time and then it will assign. Here you can see the boundary conditions are assigned. So now I will just go in the edit, and click optimize. Before clicking optimize, here I will check the conditions. Here is the loads, dead load, live load. Here is a design combination 1.4 dead and 1.2 dead plus 1.6 live. Okay, biaxial, uniform, steel design code, concrete design code, complete area. So here is the optimization criteria. So what thickness the base plate will be designed. Here is a maximum thickness 76 millimeter and minimum thickness is 6.3. Software automatically apply the increments and design the optimum base plate. So similarly, base plate dimension, here is maximum distance to plate edge. Here is a maximum distance to plate edge. Okay, and next that is the effective embedment length from the base plate to the into the concrete. You can increase according to the code conditions. So here is a member, our member, prismatic member, that is a member type, that is a material. Here is a connector. So 3D. So I have not applied any stiffener, so you can apply and increase the thicknesses all type depending upon your requirement. So in this case I am just taking without any stiffener. So that is the unstiffened condition, that is a center. Okay, so you can also study that is a weld type. So basically we have to also fix the steel column to the base plate. For that is a weld strength E70. E70 means 70 KSI. That is a weld thickness, that is a 5 by हेलो
हेलो।
हाँ जिशान, मैं ठीक है, मैं ओके निकलता हूँ।
चलो ठीक है, ओके।
E70 mean 70 KSI. So here is a weld thickness, that is a 5 by 16 inch. So with pedestral means that is a concrete footing, that is a length and width you can also optimize. I will also show. And the concrete, that is a material you can also select according to your requirement, that is a 3000 psi, 4000 psi, 5000 psi. So here I am selecting 3000 psi. Okay, that is a anchor longitudinal position. If you want to increase the number of fasteners, you can increase the number of rows, anchors. And anchor type, that is a headed. Here is a L bolt, here is a J bolt. So you can select according to your requirements. The bolt type, that is a hexagonal. Also you can, that's a very good option. You can also select. If the reinforcement are you want to also consider, then you can also apply the number of reinforcements in the one direction and in the other direction. Similarly, shear reinforcement. So now I will just click the optimize. Software automatically optimize the thickness, all the things. Here I will click optimize. In the results, all checks are almost okay. Here is the anchors effective length. Maximum value is this, value is 345 millimeter. And second is elastic method. Weld axial capacity means the weld thickness which is provided is not okay in the design combination too. So we have to see the thickness of weld length. Here is the weld length, the 3D. Here is the weld length given 5. I will increase into 6. Here you can see now the this is turning into green, means design check, or this base plate design is okay. So here I am clicking again, for example 4, it is going under failure. So now I will provide 6. Now our design is okay. For drawing, you can also generate the drawing from here. That is a top view, side view, and bolt, anchor detail. So that's how you will design into the in the RAM connection. So you can also export this drawing into DXF file. So that's all. Thank you. Hi, Assalamu alaikum, peace to you. In this video we will design a single footing foundation. So example 12.2, design a square column footing for a 16-inch square tight interior column that support a dead load of 200 kip, live load of 160 kip. The column will be reinforced with 8 number bar, and the base of the footing is below 5 feet. The soil weight is 100 pound per feet cube. Fy 60 ksi, Fc prime 3 ksi, and Q allowable bearing pressure is 5000 psf. So the effective bearing pressure 5 feet below the soil is 4400 psf. The design problem from a design of reinforced concrete from a Nielsen book. So I am going to start from a new model. First of all, I will select the unit system because our problem is in the FPS system. So I have selected the US customary unit system. So now I am going to click the grid system. Here I will put 2 grids in the X direction and 2 grids in the Y direction with the spacing of 20 feet by 20 feet in each direction. Okay, so here we can see our model. In x direction is 20 feet and y direction is 20 feet. The after calculating the approximate or area of the footing, that is 81 feet square, so I have selected 9 feet by 9 feet the footing area size. So first of all I am going to define the materials, the concrete and steel materials. So FC prime is 3 KSI and FY is 60 KSI. Here I have put 3 KSI. Okay, now I am going to define the steel bar, that is of 60 KSI. There is already defined 60 KSI grade, so I will just change the name of it, and you can also define 60,000 PSI grade steel. Okay. Now I am going to define the slab properties. Here is slab of the footing. I have selected 24 inch, which is 2 feet slab thickness. And I have also selected the type. So now I am again defining a new slab, which is the stiff portion of slab, which will show the central central portion of concrete slab, central portion of column, that is 24 inch. So first of all I will draw the slab, that is of 9 feet by 9 feet, by selecting quick draw areas around points. So here in the x direction, x dimension, I will put 9 feet, and the y dimension, that will be 9 feet. And the property is footing. So here after just one click, this slab will be drawn of 9 feet by 9 feet. Now I will draw this stiff portion, that will be indicate the 16 inch square tight column, 16 inch. The software automatically understand and convert into feet, so I will just click that portion. Here you can see it is showing that column of size is 16 inch by 16 inch. Now I have drawn the point, so where I can apply the loads. In our example there is only dead and live load, so that's why I defined it dead and live load patterns. And for the designing of the foundation according to LRFD method, so we have to define the two combinations, that is 1.4 dead and 1.2 dead plus 1.6 live, that is according to ACI code. So now I will define the boundary conditions, that is for the soil. So like I will define here the modulus of subgrade, that is basically the bearing pressure divided by the allowable settlement. So here I am defining the soil properties. In this problem, that is effective bedding pressure is 4400 psf, and the allowable settlement is for this isolated footing, that is 1 inch is equal to 25 millimeter. So here, after dividing the bedding pressure divided by settlement, that is equal to 452,800 pound per feet cube. Now I will click the slab. After selecting the slab, I will assign the support data, that is soil bearing pressure at the foundation. Now I have clicked the point and I will apply the loads. That is, dead load is 200 kip and live load is 160 kip. 200 kip. Okay. So now I will select again and apply the 160 kip live load. To check that loads have been applied successfully, you can check by clicking the right click on that point and you can see the loads. I am defining the design strips along the X and along the Y direction so that I can see the results by strip method. I will prefer to draw the design strips manually, so that's why I am defining here the strips manually. Change the name for to draw in the Y direction. Okay, now I will run design and analysis. Before running, I will save the model design of isolated footing using CSI SAFE software. After running the model, you can see the deformations according to deformation shape against the load combination 1.2 dead plus 1.6 live. Now show reactions against the load combination for the soil bedding pressure, for the soil pressure under the footing. So here that much amount of pressure is under the footing, so we have to provide more reinforcement to control the pressure, to control the movements, shears, etc. Now I am seeing the moments in the layer A of strip. In the layer B in the Y direction, here the movement is 399 kip per feet square. So also see in the book example 404 kip feet, that is okay. So Here also the same results in the y direction of the movements. In the show slab design, I will go through both methods by FEM, finite element method, and by stream method. First of all, by finite element method, in the direction 1 top D bar, in the direction 1 bottom D bar. Now strip based, only at the strips locations I can see the reinforcements top and bottom in the layer A, mean in the x direction, that is. Now in this total amount of reinforcement required. Similarly in the y, the total amount of rebar area required in the strip, so that is per square feet. So now I am providing the reinforcement against the applied loading. So here I am changing the spacing here, that's okay. Now I am optimizing the reinforcement. Apply. If I provide number 4 at the rate of 6 inch spacing, that is not enough, so I am reducing the spacing. So number 4 bar at the spacing of 4 inch in the x and y direction, that will be okay and satisfying the against the applied loading. Now I am running the detailing. Here after running the detailing, I can see the footing layout plan, footing table, and footing bill of quantities mean how much an area of reinforcement required. Here is showing number 5 bar, but I have provided number 4 bar, so I will go in the preferences and change the preference bar number 4 so that I can optimize accordingly. Column strip number 4. Here I have set in the preferences number 4 bar. Okay, now I am going to again running the analysis, running the detailing, sorry. So now check in the footing bill of quantities against number 4 bar, total 441, fit scale length required, fit length required. Thank you. For the designing of confined footing with detail, I will show in this video. File, new model. Here is the design code, design preferences, project information, unit system. Here I will select metric defaults, okay, and then I will select the blank. Then I will draw a grid. For combined footing I need only 2 grids, so that's why I'll just make 2 grids. First of all 1, 2, and the spacing will be, for example, 2 meter. That is a combined footing, so that will be near distance, and here will be 0. So you can see in the x direction data is appeared. For the y direction I will click A, click B, and with respect to x, and here will be 0. Okay, and that's the story height above means datum level is 0, and above 0 and below height is 0.14 per meter. And for the combined footing we do not need these heights. I will click OK and OK. Software automatically generate the grid system. I have zoomed the grid system. Here you can see the x distance is 0 and the x distance next is the 2 meter. So first of all I will define the slab material property and new material property, because I want to take in this example the material defined by the software. So here is a white concrete that will be 30 megapascal, and the modify and the steel grade is 400 megapascal. Okay, Okay, in this example I am taking as a default slab properties and new property. For example, for combined footing I am taking as a 140 millimeter. Concrete material will be 30 megapascal. In here that will be 450 millimeter, and it is the footing. Okay, and now I will draw one more, add a copy of this. That will be stiff column. That material property is the same, and here I will stick stiff, and its thickness will be also 450 millimeter. Okay. Now I will draw the points for the drawing of the footing grid system. So here I will draw first of all points minus 0.5. Okay, 0.5. Here is the first. Here is the second. Fourth. Third, and now fourth. Here I have drawn the points where I will draw the combined footing. Here I will select draw rectangular footing and click slab 450 millimeter, that is a footing thickness. I will click starting point and end point. That's the combined footing. Now I will click draw around points. Here I will click stiff column. That will be for I want to draw 300 millimeter column by 300 millimeter. Its thickness is same as that of footing, so that's why I have put the thickness of the stiff column 450 millimeter to match the thickness of this footing slab. So now I will click here and click here. Okay, now I will again draw a more point at the center 0 0. Why? To draw the points. So in this example I will take the soil subgrade modulus also as a default, assign soil properties, apply. Or it's not difficult, you can easily define soil subgrade modulus, modify, and here it is a 2000 kilonewton per meter. In this example I will take the allowable bearing pressure 100 equal to 100 kPa divided by 25 millimeter allowable deformation 1000. Okay, so here software calculated is 4000, compression only. Okay, I will click at the center area of the footing, assign support data, soil properties. Okay, now I will assign the loads. First of all I will click the points where I want to apply the loads. That's the load which will come from the above structure. Assign load data, point loads. Here I will apply live load, and in the z direction that will be, for example, 200 kilonewton, mx maybe 50, my maybe you can say it's about maybe 30 kilonewton meter, and the load size it will be column size. So our column size is 300 millimeter. If we do not put, software will not calculate the punching shear. It is must requirement. Okay, now I will go in the define, and load pattern is by default. For this example it will be okay. Define load combination. Default design combination, I will click on to strength and service normal. Okay, for service normal, here first combination is 1 dead, second will be 1 dead 1 live. Okay, and that's the ultimate combination. Okay, so now I will run. Before running I will draw strips, add design strip. I can also draw by default or I can draw manually. So in this example I will draw manually. Draw design grids. Okay, the width will be column strip. Here I will click the starting point. That will be X reduction grid and its name is A. Now I will click B. Its reduction will be Z. Okay. Okay. Now I will make a middle strip. If your snaps do not appear, snap option do not appear, just right click snap option. So you can select the here the points, grid intersection, intelligent snaps. So after clicking this, your snapping option will also start appearing. Now I will start the save the model and run the analysis and design desktop. CSI SAFE exercise combined footing. Okay, now I will run analysis and design. Okay, now it is a deform for dead load. Now I will see display show deform shape against the bigger service load combination. Apply. So maximum deformation is minus 86 millimeter. It means the deformation is exceeding the 25 millimeter. So we have to increase the thickness, and second we have to make the more broader area. So due to movements, its one side is settling more. And let's see also the what's the soil bearing pressure. Show reactions, soil pressure against the service normal. Apply. Okay, you can see the pressure is also exceeding. Our allowable is 100 kPa, but that's exceeding 344 kilonewton per meter square. Okay, uh, let's also check what's the punching shear. Our punching shear is okay, but we have to satisfy the allowable settlement and bearing pressure. For that I have unlocked the model. Now I will there are different ways of edit the geometry. You can do you can further see the edit geometry video. So I will also show here how I will edit the first of all I will draw points. Now I will put 1.5 meter 1.5 meter offset in the center. You can see that's the much bigger point. So no, I will take at this. First of all I will increase 1 meter. Okay, now it's much better. Here downward minus third point. Okay, now I will just click modify and click the slab, and one by one, first point, second point, third point, fourth point. Boundary conditions already assigned all the things. So and the second thing is the footing thickness. I will also increase and define slab properties, modify. I am increasing it to 800 millimeter, and the strip column thickness is also 800 millimeter. Okay, now we'll again run analysis and design. Display show deform shape against service normal. Apply. Okay, now you can see the deformation is minus 26 millimeter, which is nearly to allowable settlement 26 millimeter. So let's check again the display show deform shape or show reactions. Apply. Okay. So what's the bearing allowable bearing pressure? Now it's a 107 kilonewton per meter square. So just I will increase the little more thickness. Now define slab properties. I'm increasing it to, for example, 900 millimeter. Okay. Now I will again run analysis and design, display, show deform shape against second combination, that is a bigger one. So now the allowable settlement is still minus 27.53. That is because the soil, the footing period is also increased. So for further we have to increase the footing area. For that I am clicking on lock. Okay. Now again I will draw points. First of all, I have did the offset of 1 meter. Now I will do 1.3 or 1.2. For example, in this I am taking 1.3. Okay. The first point offset is here, then minus, second is here, minus, third one is there, fourth one. Okay. Now reshape, click the combined footing here, here, here. Further you have to also edit the design strips. Escape, reshape, click. Now make it to end from this side also. Okay. For the middle strip, here, if this go beyond the footing, it will not matter. Okay. Now I will again run analysis and design, then display, show deform shape against service normal, apply. Okay. Now you can see this is below the allowable settlement, means 25 millimeter. So our settlement check is okay. Now I will go show reactions, soil pressure against normal, apply. That will again less than 100 kPa. So it means our footing design is now okay. Now the third check, show punching shear design, that is also okay. Now I will check the show strip forces and what are the moments against the ultimate, apply. So here is the moments values in the layer A. Similarly you can also see in the layer B what are the moments, and third what are the shear forces, apply. So that's how you can see all the forces. Now I will go run and display, show slab design, layer A and B, strip base, apply. So that's the reinforcement requirement. For example, in layer A, that's how you can see at top no reinforcement and bottom is requirement. Similarly in this direction. So now impose the minimum, apply. So minimum is more, so minimum will justify the satisfaction, apply. So here you can also put the reinforcement, what spacing will be enough, for example 200 by 200, apply. So its requirement is more, so we have to, for example, let's say 16 and do it to 120 by 120, apply. Now we can also optimize by reducing to lower parts and height spacing. So that's how you can justify the reinforcement. Now there is a detailing option. You can set the preferences. I will just click the detailing. Here is a footing, just that's the grid spacing software showing. What are the dimensions? You will see in the footing. That's the footing layout, footing table. 4.6 meter is the LX dimension. LY is the 2.6 meter. 0.9 meter means 900 millimeter. So that's the reinforcement. 8 number 10 bars and 8 number 10 bars. That's requirement. Please also study in detail. So that's how you can detail the combined footing. So have a nice day. Hi, Assalamu alaikum, peace to you. In this video, we will learn how to analyze and design the SAFE, the combined footing in SAFE 2016. First of all, we will go from the zero level. I am going in the file, new model, and here is the design code ACI 31814, and will use the metric system, SI system, but you can use US default whatsoever you like. So I am hitting OK, and now from here I will select the combined footing. So there is also all other types of footings like base mat, a single footing, and here I am clicking combined footing. In the combined footing, here is showing the plan dimensions like left edge distance is 2 meter and right edge distance is 2 meter, means left edge and right edge, and top edge distance and the bottom, from top and bottom both are 2 meters, and load spacing and the spacing between two foundations is 8 meters. So whatsoever you like, you can adjust according to your desired loads and desired loading geometry conditions. And here is the loading condition. Here is P, dead and live loads 1500 kilonewton. So I am here also applying little bit movement like 60 kilonewton meter mx, and also in the load to type in 60 in here. So whatever the moments are you are having, you can put according to your desire to design the combined footing. So I am here putting the footing thickness 600 millimeter, but after in the main window you can change according to your needs. So here I am putting the subgrade modulus. Subgrade modulus basically to model the foundations to make the real conditions. Like in the real conditions, we are having the bearing capacity, allowable bearing capacity, and the allowable settlement. So I am here going to show you how to calculate the soil subgrade modulus. In the soil subgrade modulus is equal to pressure over deformation. Pressure is basically allowable bearing capacity, which we get after from the field testing or from the laboratory testing, and the deformation is the allowable settlement in the foundation. So whichever type of foundation you are designing, so according to that the allowable settlement you can use. For example, in isolated footings you can use 25 millimeter, and for the mat or raft foundation you can use 50 millimeter as a allowable settlement. And now here I am showing the calculation for the subgrade modulus, and allowable bearing pressure is the 200 kPa and allowable settlement is 25 millimeter. The soil subgrade modulus will be K is equal to 200 divided by deformation is 25 divided by 1000 to convert into meter. So here I am getting 8000 kilonewton per meter cube. So I will put in case of in this case of modulus of soil subgrade modulus 8000 kilonewton per meter cube. Okay, so after hitting OK, you can see the footing, and as you have as you want to model in the CSI SAFE 2016 software. So before going further, I will first draw the design strips, add design strips. So here you can do by automatic, or you can also draw by manually. Like here I am drawing the design strips. Here draw design strips strip layer is A, and from here to there, and in the other direction I am naming it B, from here to here. Why I am doing this, assigning the design strips? Basically, the software design the foundations in two ways. One is FEM, finite element method, and second is the strip design method. For the strip design method, we have to assign the strips like I did now in this foundation. And now I am going to save this model with the name combined footing design. After saving the model, we have basically applied the loading successfully and the boundary conditions, like we have defined the soil subgrid modulus. We can also check again, define in soil subgrid modulus, and here is the soil subgrid modulus which we have defined, soil 1. Here is 2, but here which we defined soil is 8000. Okay, now we can check. We have defined the soil property, soil. Okay, before running the analysis and design, I am going to define the load combinations. There are two load combinations already defined, so I will just delete them, and I will assign default design combinations according to service normal conditions. Okay, and you can check the load combinations: one dead, one live, and one dead. So in the design combinations, design preferences, you can see the covers, as for example these are slabs, so prefer bar size whatsoever you want. Okay, in design combinations we will select service, we are designing according to service normal. Okay, so now I am running the analysis and design. So after running the analysis and design, you can see display show deform shape against load combinations. Apply. Here is the maximum is 8 mm, which is less than 25 mm, so it's okay. Again this again second combination, again the settlement in the foundations at all the points is less than 25 mm, which is okay. So now I am checking the bearing pressure, show reactions, soil pressure against apply. Here is at maximum minimum are less than 200 kPa, so it's okay. So for second combination, that's also okay. So now I am going to check the punching shear design check. So the punching shear design checks are less than 1, so that's are okay. So here are basically 3 checks: pressure under footing less than 200, okay; deformation under footing less than 25 mm, okay; and punching shear is less than 1 is also okay. Preferable should be less than 0.9. If you are failing in any check, go towards the inputs like geometric. It means you have to change length of the footing, width of the footing, and thickness of the footing, and you can also change the material property like concrete, compressive strength, etc. So here now I am going towards the design. So all checks are okay. Show slab design. In the show slab design, there are two methods of design basis. One is FEM, second is strip based. In the FEM, you can, for example, you want to see the top reinforcement, how much is required. So here you can see the top requirement of top reinforcement. So like in the bottom, here under the footing, bottom reinforcement required. In the middle, no. Same way in the second. So I will prefer in the strip based. In the strip based, for example, in the layer A and layer B. Apply. in the x direction layer A. Here is the footing area required 1561 millimeter square per meter. So in the y direction is the B strips. Here you can see the top and bottom reinforcement requirement in the y direction. So I will just apply. Here is the required reinforcement in the top and bottom direction of the combined footing. So I will just provide, for example, number 12. Here the rate of 250 millimeter spacing, but this provided reinforcement is still less than the required. So I will just increase, for example, to 20 apply. So still in the reinforcement, what reinforcement? Top I am just decreasing the spacing it to 150 apply. So now it means if we provide this reinforcement, I am just showing the demonstration video, so you can change according to the desired or optimization way. So here you can see, and also there is one beautiful function of detailing. So in the detailing you can see the drawings. Okay, drawing sheets, cover sheet showing the notes, footing layout plan, footing table. Here it is showing, for example, these are bar A, bar B, and total thickness is 600 millimeter, so that is 0.6 meter. LX ran by geometry dimensions, and footing, for example, F1, so it's 22 number 14 bars and 18 number 16 bars in the A and in the B directions. So that's all. Have a nice day. Design of raft/mat foundation in CSI SAFE software. In this video, I will discuss step by step for the designing of mat/raft foundation. Here I will click File, New Model. Here is the design code. You can select according to your country. Design preferences. Okay, code. These are the design factors. Please do not change these factors. And minimum cover slabs. If you are designing the foundation, please make it 50 millimeter, which is 2 inch. The preferred bar size that we can change it later, but here right now it's a 16 millimeter, and that's the rest of we left, and that is the minimum cover of beam post tension. Okay, then project information, you can put the project information. Okay, then here is the unit system. I will select the metric. You can select FPS system, but here in this problem I'm selecting the metric system. Okay, then there are options. I want to start from a blank, from a templates that are present, from a grid only. So I will definitely start from a scratch file from 0 level. I will click blank document. Okay, now I will define the grid system. Edit, add/modify grids, modify spacing. Okay, so here I will define one by one grid: A, B, C, D, E, F. Okay, here is the spacing between the grids: 5, 6, 6, 7, 5, 0. Okay, now for the y grid data 1, 2, 3, 4, 5, 6, or you can do it more, 7. The spacing is 7, 6, 6, 5, 7, 6 and 7. Okay, that's the grid. And general grid data, I will just illustrate you some how it works. You can draw in the inclined grids. For example, I'm making x1 and the point is 0, 0, and that will be, for example, 15 comma 15. Here you can see I can draw the inclined grades according to my requirement, but I do not need in this problem, so I will just hide it. Click hide. Okay. Now the rest of the grid is appearing. The inclined grid is not appearing because I have hide that grid. So now I will define the material property. Here the predefined 30 megapascal concrete. So I will take it as, you can define the new material, and the grade 420 megapascal, 400. So I will making it to 420. 420. Ultimate will be 620. These are the 60 grade steel. Okay. Now I will define the slab property and new property. Here I will define the mat foundation. Mat, that will be, for example, of 700 millimeter thickness. Mat foundation 700 millimeter. Okay. Now I will define for the stiff columns. Add copy of this stiff column. Okay. Now it's a stiff column. Its thickness will be also 700 millimeter. Okay. Now before drawing the grid, I will check the load pattern. Define load patterns is dead and live. You can add more, for example, wind, snow, etc. Okay. Define load combinations. I will click add default design combination. Strength ultimate and service normal. Service normal are 1 dead, 1 dead plus 1 live, and these are the strength combination 1.2 dead plus 1.6 live. Okay. Now for drawing of slab, there are different options. Now I will select draw slab from here. That's the property straight line. You can also draw the inclined, curve, or multilinear slab. So in this example I will select straight line. I will start from here. That is a mat 700. I will click enter. Software automatically draw the mat foundation. Now I will make the offset, because when columns come here, then the 50% column will be outside, so more than 50%. So to make in the grid, we have to make the offset of the slab. I will select the slab, edit areas, expand slash link. If I will put positive value, then the offset will be outside. If I will put negative value, the offset will be inward. So here I am making the offset of 1000 meter, but means millimeter means 1 meter. Okay. Now further I will for the drawing of columns, I will select quick draw columns. Here I will select stiff column, and dimension of column will be 450 millimeter by 450 millimeter. Okay. Now I will draw each column. Okay. Please make sure when the joint appears, then click press. Here when the joint appears, I will press the left mouse button. Okay. I have drawn all the columns. Now I will make the center points. Here when I click, basically the 4 edges are selected. I was unable to select the center point. For that purpose, I will draw the points. Draw points with 0 offset at the center. Okay, so that's how I will draw for whole slab. I have selected all the points. Now I will go assign load data, point loads, and I will select live load, and in the point loads I will put the column dimension for 50 millimeter by 450 millimeter for the calculation of pump punching shear. And in the gravity load I will apply, for example, 1000 kilonewton downward load, and the moment is, for example, 230 kilonewton in the x direction, and the y direction maybe you can take it as 300 kilonewton. Okay, so these are the loads will be applied on each column. Okay, you can see the values in 3D here. In each column load has been applied. Okay, now I will define the soil subgrade properties, which is soil subgrade modulus. Modify. Here I will put the soil subgrade modulus. Here is for soil subgrade modulus, that is a pressure over deformation, means allowable bedding pressure over allowable settlement in the foundation. That values will come from geotechnical report. For example, if we have allowable bedding pressure, that's a 200 kPa, and the allowable settlement is 25 millimeter, then the soil subgrade modulus will be 200 divided by 25, that is the settlement. For example, in this case, that the allowable settlement is 50 millimeter. Here allowable settlement for isolated footing, that will be 25 millimeter, and for the raft/mat foundation, that will be 50 millimeter. So here now I will put 50 millimeter and 1000 for the conversion. 200 divided by 50, answer will be 4000 kilonewton per meter square per meter. So that's the value I will put in the soil subgrade modulus. That will be 4000 kilonewton per meter cube. For the designing of foundation, please check the compression only. Okay. Okay. Now I will make in the plan and select the slab. Okay, you can see I have selected the whole mat foundation slab. Assign sport data, soil properties. I am assigning the soil one, which is I have defined 4000 kilonewton per meter cube. Okay. Okay, now you can see soil have been assigned in the yellow 3D. Okay, here you can see soil applied to the whole foundation. XY in the plan. Now I will apply design strips. Edit, design strips for the design by strip based method. Okay, in the X direction you have seen grids have been drawn. Edit, add design strips and draw in the Y direction, and the value will and the label is strip layer label is B. Okay, you can see, but here is some issue that software is not making the strips to the end. Please make it by clicking edit shape command. Click here and make it at the end. Similarly this one. Please make all these so that you can see the detailed design by now I have extended all the strip layers to the end points so that we can get better results. Okay, XY. I have assigned the loads, boundary condition, strips, load combinations. So now the step is run analysis and design. Okay, mat foundation. Okay, now I will check the deformation. Display show deform shape. Load combination for service normal. Apply. So the maximum deformation is 27 millimeter. Allowable in the mat foundation is 50 millimeter. So here the maximum deformation. Okay, now I will check the soil pressure against normal load combination. Apply. Okay, so the maximum pressure is 108 kPa, so that is also less than 200 kPa, so it means our beading check is also okay. Now I will check the punching shear. For punching, all the checks are also okay, which is less than 1. So for checking of any check, right click, so all the information will appear. Unbalanced movements, maximum design shear stress, which is coming from the applied loads, concrete shear capacity. So punching shear is that is 0.88. Okay, now I will go in the display, show strip forces. I want to see, for example, movements. Apply. Now I am seeing in the layer A. So here is the movement values. You can see these are for middle strip, these are for column strip. Similarly for Y layer, apply. So here you can see, so that's why we extended at the end, so that we can get the results. Okay, similarly for shear, you can see the results. Okay, now for reinforcement design, I will go in the show slab design. For example, either by final determinant by strip base method. Here I have selected this layer A and B. Apply. So okay, for example, let's see for layer A in the x direction. So here is a top and bottom reinforcement requirement. Okay, let's see for layer B. Similarly, you can see if I impose the minimum, apply, so you can see almost minimum is governing the criteria. So here some is the more enforcement. So what bars are required, how much enforcement spacing should be. So here is the options. Here for example I will select 16 millimeter bar. Apply. So let's reduce the spacing 200, 16, 200. Apply. No more. For example I am reducing 120. I am just making more or less just for the studying. You can optimize much better. Okay, so here is a additional enforcement is required. You can provide extra bars in these portions. Okay, so now I will show how to detail this lab. I will run the detailing. There are multiple preferences, what bar you want to show in this lab, so all these things. I will click run detailing. Okay, here is a drawing, slab views, framing plan, rebar table, rebar schedule, bill of quantities. So 27 metric ton reinforcement will be required. Individual mat view, rebar plan, top rebar plan, bottom rebar plan. So here is the strips, and the strips in the x and y direction. Spacing are provided here. Top rebar plans. This is the mesh. How the bars will be look like. Here for the bottom. Here is the section of the mat foundation, and that's the profile, reinforcement profile. Reinforcement profiles are, for example, here, for example, in this portion, the required is, for example, the that's the this green section is basically the our enforcement. The blue is the required enforcement. So that's the provided enforcement. The software is saying here the provided enforcement is 16.6% more. Here is 9.5% more. Here is 202% more. So that's the profiles for both, for layer A, for layer B. Okay, so that's all for the designing of mat foundation. Hope you got all the ideas about the mat foundation designing. So that's all. Thank you. Have a nice day. To check the uplift of raft foundation, there are two ways to create the combination. One is you convert the default combinations into uplift, nonlinear uplift, or you can create in the load cases. For example, define load cases. Here is a dead linear, live linear static. Modify. Here you can see. But I will now define one new load case that will be uplift. Okay, and here I will select nonlinear allow uplift. It's a constant. So for the convergence of results, so here I will put the coefficient for dead 0.9. I'm reducing the dead because I am allowing to the software to check the uplift pressure. So here live is 1. So if there is earthquake, you will also apply one time with positive value, one time with negative value, but check in both directions. So here I have defined the uplift check. Okay, and that is a non-linear allow uplift. Okay. Okay, now I will run analysis and design. I will check two things, the deformation and the pressure. Now the analysis is complete. I will click display, show deform shape against uplift load case, apply. Okay, so let's see. In the results, all the values are in the negative, means all the deformations are downward. If there is any positive value, then the deformation will be upward, means the one edge will be lift up. So in this our case, our all the deformations are in the negative, means downward, so no uplift in the settlement or deformation. Now I will check show reaction forces, foil pressure against uplift case. Okay, here again that's the pressure all are negative, so means there is no uplift. If there is any positive values, and then definitely there will be uplift. And how to counter uplift? You have to increase the weight of the footing by increasing the thickness of the slab, or you will also increase the dimension if necessary. So that's how you will counter the uplift pressure. And the second way of creation of uplift pressure combinations is by default. Okay, I will go in the define, convert combination to nonlinear uplift load cases. Here is a two uplift for load combination. Two are ultimate and two for normal. And for normal, I will select the load combinations. Okay. Here, the software two combos were selected and two combos were converted into non-linear uplift cases. Okay, I will see is it created or not. So load cases. Here you can see two non-linear cases have been generated. Okay, modify. Here you can see non-linear uplift. So here that is 1. So we have to make it 0.9. Okay, and similarly the second load combination converted by the software automatically, that is also 0.9. Okay, then same way you will run analysis and design and check the bearing pressure and settlement. So that's all. Have a nice day. Thank you.
In this video, we will design of TV studio with width of 15 meter and length of 30 meter with upstand beam with a clear height of the hall 12 meter. In the hall, no column is allowed. The hall basic dimension is 15 meter wide, 30 meter long and 12 meter high. So let's start with the new model in the eTabs software. So after clicking file, the new model, and this in the blank space this window will appear. After that we will define the grid system in which we will draw our beams and column members. So I am going to define the grid system here. In the grid system, in the story data, first of all in the grid system I am going to modify. So here I am defining the grid spacing and the grids in the X grid data A, B. For example, it's 7.5 meter, 0.5. Basically we have to cover 30 meter. For that purpose 15 meter and 15 meter will become the 30 meter. And for the grid Y grid data 1, I am taking the ID 1 and it is 7.5. Okay, now we can see 15 meter width and 30 meter long grid we have defined successfully. Now I am going to define the story data in which I will define the story height. So basically I will define two stories to define the bracing height. For example, each story is 6 meter and 6 meter, which will become 12 meter. Okay, so now I can see it's a 15 meter. Let's see in the plan of story 2, apply. Okay, so here we can see it's a 0 0. Here you can see the coordinates 0 0. Here is 30 meter long, and in the length, in the width wise it's 15 meter. So in the elevation, see in any type of elevation, here is you can see z is equal to 12 meter. So we have successfully defined the grid system. Now let's define the material and the cross-sectional properties of the structural members. First of all, material property, there is already defined the rebar, which is steel material, and Fc prime 24 megapascal and Fc prime 28 megapascal. I will define a new material with Fc prime 20 megapascal, a new material. It's a concrete material. So I will, as it is already pre-default concrete, its members strengths are defined. So we will define user according to our needs. Fc prime 20 megapascal. So here in the design property data I will define 20 megapascal. Okay, so here I have defined another concrete strength material, Fc prime 24, 28 and 20 megapascal. Now I will define the bar, add new material, steel, basically used for steel cross section members, but for reinforcement we use rebar. So I will define the rebar of grade for 20 megapascal, grade for 20 megapascal. So here I will change for 20 megapascal. Okay, so here we have defined for 20 megapascal because there is already, but I showed you how to define the material of steel bars and concrete strengths. Okay, now I will go in the defining frame sections. In the frame section there is two already: automatic beam selection, beam column selection. We'll try to this here. Here is the beam 225. I will delete and define again. Add new property from concrete, a rectangular cross section. Here I will define beam 225 by 225, and here I will define 225 by 225. And what's the material of this beam? I will select from here 24, 28 or 20 megapascal. I will select 20 megapascal, and I will define whether it is a beam member or a column member. So I will select from the reinforcement tab. It's a design type column, not it's a beam 225 by 225. Here I can select the grade of the steel, whichever I want. So definitely I will select grade for 20 megapascal steel for SI system. Okay. So here is define. I have defined another beam. So I will delete again a column and define again to show how to define a column in eTabs. Add new property, concrete column, concrete rectangular cross section. Here is COL for column rotation 300 by 300. So I will select the material property again, rebar for 20 megapascal, and define the cross section by defining its dimensions 300 by 300. I will select material, it's a column, so definitely concrete strength of FC prime 28 megapascal, and I will go in the modify column for 20 by 420. I will select 3 in the X direction, 3 in the Y direction. Maybe I will select a little lower. These are trial reinforcements in the longitudinal direction, in the confinement direction. Basically, we will reinforcement to be designed. We will check at the end the reinforcement designed by the software. Okay. Here is defined. I have defined the column 300 by 300. Here I will also define for all the beams auto beam selection, and for columns auto column selection. Software select from all the lists, like I will show auto select list, auto select beam. In the auto select beam concrete, I will select all the beam under the heading of auto select beam here. So first, for definitely I will start the trial from beam 225. Software automatically perform trials first of all in 225 millimeter beam, then 300 by 300, 300 by 450. Software automatically optimize which beam member is suitable at any location. Similarly, we will define auto column, auto selection column, auto selection column. Okay, selecting the material property, it's concrete. So from here I will select all the columns which I have defined, add here, modify, start definitely from column 300 by 300. I forgot to define the modifiers. For example, I have defined in all the columns in the beams and column members. For example, in beam 225 by 225, I didn't define the property modifier. So here I will put 0.35 moment of inertia. Why? Because in the ACI building code requirements for structural concrete and commentary, ACI 318M14, moment of inertia and cross-section members permitted for elastic analysis should be moment of inertia 0.7 Ig for columns, and for beams 0.35 Ig, and for slabs 0.25 Ig. Because in the concrete members we consider the crack cross-section members. because we do not consider the concrete area which is in the tension side. So that's why the code refer that use the moment of inertia, correct moment of inertia like these 0.7, 0.35 and 0.25. 0.35 for beams and 0.7 for columns. So that's why I have changed the moment of inertia 0.35. Okay, and I have not defined also in the column 300 by 300 modify property. Here I will put 0.7, and in the two direction also, because in columns both moments are usually present, mx and my, so that's why I define in both directions. Okay, you can also check in all the beams I have defined that property modifiers in the beam 0.35, and in the column, any column, you can check that I have defined the property modifiers. Okay, so after that, defining the beam material and cross section material, there is one last thing we have to define: the slab section. Here is already two slab section have defined. I will define a new add property. Slab material, I also select 28 megapascal, slab size of 175 mm, and I am putting here 175. Here there is different types of slabs: drop, draped and waffle slabs. We will select simple slab and hit OK. So here I have also defined the slab property. Now after defining the slab material, slab cross section, column cross section, beam cross section, now I will go towards the drawing of the members in the grid system. I will go in the plan, in the story to apply. Okay, from here I can select draw beams and column, and here is the option quick draw beams. I will select quick draw option, quick. So here I will select the auto select beam, because auto select beams all beams are present. Software automatically optimize the cross section here, and definitely check that it's a one story. So I am going back. I will select all stories and then draw. What will happen, you can see I will drawing in the story 2. Automatically in the story 1 there is a drawing of the beams happening. So I will again go back to story 2 plan. Okay, here, so in the center of the hall there should not be any beams or columns, so that's why I will just select one story and then draw beams. Okay, now I will define draw the, now you can check that I have defined the beam members. Now I will define the column members at the perimeter only, because no column is allowed in the center of the hall. So now I will select auto selection column. So here from this option, sorry, I will select auto selection column, and here I will draw one by one column, not only in one story, in all story. I will do undo, and after that I will select one story. When I click on this, automatically all column will draw in the lower story also. Plan, apply. Okay, so I will define the columns only at the perimeter. After that, only slabs are required, so I will click quick draw slabs. So I will select the property which I have defined, slab 175 millimeter, not in all stories, only in the one story. here, 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 here. So it's a very quick process. So now we can check we have successfully modeled our uh, TV studio. So I will change the boundary conditions to make the spots fixed. Plan, base, apply. Okay, so here you can check the spots. I will select all the spots. After selecting all the spots, I will go to assign joint restraints, select fixed spot, apply. Okay, now you can see the all spots at the under the columns are in the fixed condition. Now I will define the loading in the panels. Apply. Okay, after selecting the panels, all the panels, I will go to assign shell loads, uniform load. Basically it's in kilonewton per meter square units. I would like to apply the load in kg meter. Okay, again I am going back towards the uniform loading. Here you can see kg per meter square. Now I will define 50 as a super dead load. Apply. Again select get previous selection, which is I have a little time before selected. So now I will apply live load. Apply. Okay, so you can check in each slab both loads are present by right clicking on any member on any panel. So in the loads you can see there is a dead uniform load 50 kg per meter square and live load of 300 kg per meter square. Okay, define in load patterns we can see there is a two load defined dead and live, and there is a dead weight self weight multiplier 1. It means software automatically calculate the self weight of the members of slabs, columns and beams, etc. So that's why here is a one option. So dead and live loads. Okay, so now I go towards the load combination. So there is two combinations, dead and live, 1.2 dead, 1.0 live. There is already defined. I will delete and define again. Add new load combination, 1.4 dead. So here is dead. I will just multiply with 1.4. Okay, now I define another load, another combination, 1.2 dead plus 1.6 live. Here I will define the multipliers, 1.2 and live 1.6. Okay, now I have also defined the load combination successfully. Now after defining all the things, I will save the model. After saving the model, I will run analysis. Before running analysis, you must check your model that is the model successfully correctly model. So I will go towards select all. Okay, if there is any overlap of the members, any issue, here warning messages will appear. So no warning messages were generated, so that's a good thing. Our model is successfully generated. So here in 3D you can check. Now after applying the dead loads, each and everything, now I will go towards the analyze. So here is run analysis. After running analysis, we can it automatically display the displacements against dead in meter. So I will just change the unit system into metric SI. So here you can check, here is the deformation, much more deformations. So let's check the shear force and bending moments in the frame. In the normal gravity loads, we will for the moment we click on the moment 3 apply. Here we can check in each member the movement, what are the movements and For the share, we click share to apply. So here we can check that in each member what is the share. Okay, so all things, we can also check the details forces by right clicking on any member. Here I right click the, here I can see the shear force at any location. For example, the total length of the member is 7.5 meter, so I can check the shear, moment and deflection, etc. Done. So now I go towards the designing, concrete frame design, view, revise or preferences, etc. Here are the preferences. We are designing the concrete members according to ACI 31814, and there are also other conditions like what will be the factor for the tension control, compression control, and etc. etc. Okay, and now I will go towards select design combinations. So definitely two design combinations we will select. So after this we go towards the start design check. It will take some time because we have selected the auto beam selection. It will optimize that which beam section is suitable. So it will perform many trials. So after performing many trials, it will show that which members are suitable for our design purpose. Here, analysis and design section different for 8 group members. Do you want to reiterate analysis and design? Yes. Because the design member is different from the analysis member. So software is trying to confirm that the analysis section should match with the design section. So that's why the software performing the design analysis again and again. So now the 4 members are remaining only. Again. Here in the plan. Okay, we can see the members are showing the longitudinal reinforcement. For example, we click that member and here we can see the bottom steel, the top steel and the shear steel, etc. I am hitting OK. We can check what is the shear reinforcement. Here is design shear, design moment. So in this summary we can check all the details like what is the story level, what is the beam element ID. Here it's a beam 450 by 750. The software automatically optimize these sections. So here we can see the shear is 24 and the shear capacity is 204. Definitely it's much larger than the applied shear. So here is a torsion, so no reinforcement is required. Longitudinal reinforcement. Now we can see the shear reinforcement display design info. So here in the output we can see longitudinal reinforcement, rebar percentage, apply. So here in each member rebar percentage is showing. The software basically show the reinforcement at 3 locations in each member, 1/3 and 1/3 to 2/3, 2/3 to and at 3/3 position. So let's check shear reinforcement, apply. So here is showing 0 0. Okay, so at the end of the design there are 2 checks. verify all members passed. So it's showing all members have been passed successfully. The last condition is verify analysis and design sections. So here analysis and design section differ for 16 concrete members. Do you want to select them? Yes. So here are the members which are different. Analysis section are different and design section are different. So for that purpose we have to make some changes. So I am going to make some changes, like I am applying here. Let's check what are the members here. Summary. So currently here is a beam 450 by 600. So I am going to apply here a stiffer member. So I have selected, and I am going to select the center one so that my perimeter beams become stiffer. So I am going to assign frame section property. I am going to assign 600 by 1100. Apply. Okay, the rest of the beams are in the under auto select beam. So but the perimeter beams are now in the condition of high stiffer members. Now I am again going towards the analysis and design. First I have run the analysis. Then going back towards design. Here now only 4 members are differ from the design and analysis section. It is taking time, but don't worry. After performing reiterations, it will show. Now we again going towards the verify verify all members have been passed. Okay, verify that all the design analysis section are same. So now analysis and design sections match for all concrete members. So for study purpose I have just shown that we can change the arrangements to pass our members. So that's how we did. So now after designing we can may study more, like I am going to check this member by right clicking. So its location, for example the member is designed against this combination and the bottom steel is this, and shear reinforcement no needed. So let's check in this summary. So this is the beam, this is the section, this is section properties BH, and material property EC24 and FC prime FY. What are the design code parameters? And here is design moment. So the positive moment is 1948 kilonewton meter. So against that the positive rebar is 6925 millimeter square. So any person calculate the number of rebars, like he may select number 25 bar, number 32 bar, and after that he can calculate the number of bars. Similarly in the shear and in the torsion. So there is no requirement of shear in this beam, so definitely we will provide the minimum steel of shear reinforcement flex checks in any other member. So in this member, again in this member summary, so there are many members in which shear reinforcement is not required. Let's check in the in the column members summary. So here in the column, again only the flexion reinforcement is present. So okay, so we have successfully analyzed and designed our members. Now we will go towards the designing of the slab and of the foundation. Now for the designing of the slab and the foundation, we will export the slab app into the SAFE software. Here is CSI SAFE software. So now I am going to do export in the SAFE. So first of all, for the designing of the foundation, I will export all the column slots, etc. Live, okay. Select the load combinations, okay. So here foundation and slab design. First of all, foundation design only. Here foundation, save. Now I will explain. Now up till now I have only exported the foundations. So now I am export the slabs. Basically put all the story level to file, export story level 2. On that story there is all the slabs are present. So I have selected all the loads. I am clicking OK. So I will again create new folder for slab design. Click OK. In this I will slab, save. After exporting, now I will close my model and open the CSI SAFE software. After opening the software, I will import SAFE model. So basically my SAFE model is present in the folder foundation design. So this is the exported the location where I have exported our foundations. So I am clicking open, selecting the model. So this is the grid system as we have seen in the ETAP software. So at each column foundation we will provide the spots, foundation slabs, etc. For example, I am going to define the material. So here is already defined CSA. I am going to define new material. I call 28 megapascal of concrete material. Here's modulus of elasticity. Here's a 30 megapascal. I am going to define 28. Okay. After defining, I will define slab section. Slab there is already defined. I will just modify it. It's a 200. I will define 600 millimeter foundation depth slab. So select the material 28 megapascal. Okay. After that, I will just draw the slab. Here is a quick draw slab areas. Here is again quick draw area around 8 points. I will select quick draw slabs. I think this option is good. I will select 2 meter width by 2 meter length foundations. Now I am going to draw here one foundation here, and here. So these are the foundations at where our columns are present. We can check the loads. For example, I am clicking here and right click. Here I can check the loads. The loads are successfully imported from the ETAP software. Dead live. Okay. So after defining, I am going to define the boundary condition. For boundary condition, let's suppose we have the soil capacity 200 kPa and allowable settlement 1 inch, which is equal to 25 millimeter. So to make the stiffness or the spring constant, K is equal to 200 divided by 25, 0.025. The answer will become 800 kilo Newton per meter cube. Kilonewton per meter cube. So here I am going to define the soil subgrade properties. It is already defined. I am going to define a new property of soil. So in our case it's 8,000 soil capacity divided by bearing capacity divided by allowable settlement. Here is our soil 200 megapascal. I am clicking OK. Now after that I will select all the slabs, foundation slabs, and assign spot data soil properties slab 2 and 200 GPa. Okay, so at under each boundary conditions is defined successfully. Now I will define the load combinations. Here is the load pattern again, dead, live, etc. So I will just select the load combinations. These are the load combinations for the design of our foundation. We will select the service load combination, so these combinations will not be needed. I will define the combinations just for service normal. Okay, means one dead, one live. Okay, so now after that I will save the model with the foundation design. Save. After saving the model I will run the analysis and design. Run analysis and design. First it will run the analysis and automatically after that it will run the design. Okay, so after that we can see the results like display show reactions. Definitely that will be the same. Show slab design, show punching, shear design. Like here the applied load divided by the applied loads divided by the slab capacity if it's less than 1. So our punching shear is all in all the slabs is okay. Show the slab design. So for the strip base now we will check the FEM finite element design. Top rebar, apply. Here we can check on each slab what is the top rebar. So there is much more reinforcement, millimeter scale per meter. At the center there is less, and as we going the away from the center there is much more required in the one direction. So let's check in the two direction. Apply. Again in the top also require much more reinforcement. Let's check in the bottom. The bottom needs 2000 millimeter scale in the two direction. Apply. So basically in X direction top and bottom, in the Y direction top and bottom we have checked by FEM method. Apply how much reinforcement is required. Now we will check by strip method. By strip method checking we have to define the strips. So let's add it. Add design strips, or you can draw design strips. Draw design strips. So here for example I am defining from here to here. enter. Second, from here to here, enter. First I am defining in the y direction. Okay, now I will define in the x direction. Here, now we have defined the x direction strips and y direction strips. So let's check again, run the analysis and design. Okay, display, show slab design. In the slab design, now we can check the strip based. So in the strip base, we can showing the top and bottom rebars apply. So here, when for example, let's check, it's a more simple one. Here, this in this strip, so here at the top, reinforcement requirement, and this is in the x direction. Okay, this is the both top and bottom. Let's check only top, apply. So here is showing the top. Let's check only bottom. So what are the reinforcement in this? Now we are checking the bottom, top and bottom in this direction also. Apply. Okay. Now I will again save the model. Basically we have also designed successfully our foundation. Now I will design the slabs. Okay. Basically I will again import. Now I will go into not foundation design, the slab design. Here is the TV studio, open. When will open, now it's in the new window. Now I can see in the 3D. So these are the columns, this is the slab, and this is the boundary conditions which are showing this. Under these are the columns. So for this purpose, we have to also define the I have to define the strips. So edit design strips, add design strips, for example in x direction and strip layer A. Okay, so here you can see now again design strips in the y direction. Now in the y direction by label B. Okay, you can see also. After finding these, let's define the load combinations. So there is already load combinations are present, that's good. So for the slab design we have to must check for the ultimate load, so that's why we have selected the 1.4 dead and 1.2 dead plus 1.6 live combinations. Now each and everything is defined successfully. Now I am going to save the model in the slab design folder, TV studio slab design, save. After saving, I am going to run analysis and design. It is showing the deform shape displacement dead millimeter against the red load. So we will check the slab design, show slab design. So we can check the reinforcement just for top rebar in the layer A, apply. Here you can check the top reinforcement only present at the support, and in this spot. Okay, and now in the B direction, apply. So here you can also see basically it's showing the top and bottom. That's a good thing in the one time. Okay, so now we can also see the detailing. Now after I am going to run the detailing, so we can check the reinforcement bars in each slab also. Run detailing, it will just take few seconds and generate the drawings. So here this is the drawing list, what type of drawing is generated. Slabs, beams, properties, data. So let's check the slab views. This is the framing plan, this is the rebar schedule, quantities showing less. So here is basically slab. This is showing the slab views. This is basically individual slab views, like slab 1, which is we have defined the 200 millimeter slab. So this is the showing the rebar plan of all top, bottom, x and y. So for the top rebar plan, here is only top rebars. For example, we can see in detail. For example, here from this space to this, and what are the notations you can check in the general drawings. So for example, here this section, for example, first of all check what is the sections here. One section is here and one section is here. So let's check, this is section 2. So let's check section 2. So here in this slab is showing section top reinforcement on the spot and bottom reinforcement passing, and again top reinforcement at this spot. Let's check in this section 1. Here see the reinforcements. So that's all for the slab design. For the more details you can check in the in the documentations. You can check the manuals, like here are the verification manuals, design manual, reinforcement concrete, all tutorials etc are present. You can also visit YouTube for more videos on the slab design. So thank you, that's all. Allah Hafiz.
In this video, I will show you how to model, analyze and design the strap foundation in the CSI SAFE software. In this example, I will use the previously defined data. For example, define material property 24 megapascal concrete, reinforcement for 20 megapascal, and for the slab properties, I will use footing 300 millimeter and stiff column is also 300 millimeter. Furthermore, I will use the same soil subgrade properties data that is defined in the previous videos. Here, the allowable body pressure 200, allowable settlement is 25 millimeter. The same data and the soil subgrade modulus is 8000 kilonewton per meter square per meter. Okay, and the beam properties here modify. Here is a predefined concrete beam that is 300 by 600 millimeter. Okay, the beam material will be concrete 24 megapascal, rebar material will be 420, and rebar material for shear will also be 420 megapascal. Here all the data for the rectangular beams. So here is the cover top to the centroid, so that is 75 millimeter, that will be okay. Okay, so now here is a grid data defined x in the x direction, two grids 1 and 2. The distance between the grids in the x direction is 4 meter. You can check here in the status bar, that is a x0 y0 z0. In the x direction, x is 4, y is 0, z is 0 in meter. Okay, for the drawing of footing, I will click here quick draw footing, and I will draw a 1.5 meter by 1.5 meter footing, and I will click 1 point here and 1 point. Okay, so now I will click the stiff column, that will be 300 millimeter by 300 millimeter. Okay, I will click at the center Now for the deselection mode, or press escape key. Now I will draw the center point. At the center, draw points here at the center, because I want to click these points and then apply this load. For that purpose I have drawn the points at the center. Escape. Now I will select the slab, both slabs, or both footing slabs, and then go assign spore data soil properties. That is a predefined 200 megapascal, 200 kPa divided by 25 millimeter settlement, allowable settlement. Okay, so here you can see soil properties have been defined. Furthermore, for the applying of loads, I will click the center points. Here I will apply, for example, assign load data point loads. For example, I will apply live load of, for example, 120 kilonewton downward. Okay, and for the only left slab, on the right slab, right footing, I will assign load data point loads. For example, now at existing load, or here I will click 0, and the mx moment may be 33, and the my moment maybe you can take it as 20 kilonewton meter. Okay, now you can also check that these loads have been added to the previously load. Right click at the center, go in the loads. Here you can see the point load and the moments have been applied successfully. Okay, now loading conditions are already defined, all the things have been defined. Just check the load combination here. Service load combination and ultimate load combinations have been defined. Okay, now I will run the analysis and design. Okay, now see display, show the form shape against the service load combination, apply. Here the maximum settlement is 16 millimeter. Further it is within the limit. For example, if it goes beyond, what will happen, or how you can handle by strap foundation. That is a maximum 16 millimeter. So now let's check the soil pressure. How much is the soil pressure? Apply. Okay, so maximum soil pressure is 134 kPa, kilonewton meter square, kilonewton per meter square. So that is again less than 200 kilopascal. So if, for example, in your footing that soil pressure is exceeding or settlement exceeding, and your footing is corner footing, for example, let's make it corner footing. Okay, so here is a calculator, sorry. Okay, so our footing is 1.5 meter. 1.5 divided by 2. Okay, that is 0.75 meter. It's the center. So if we have to move the footing from here to here, I have to minus 0.15 minus 0.15, that is the half of 300 millimeter. Okay, 0.6 meter. So it means I have to move this footing in the left direction. Select this footing and edit, move points or slash areas. Here I want to move in the negative x direction, so that will be minus 0.6. Okay, so here you can see footing, now it's become the corner footing or edge footing. So now let's see what are the results. Display, show the form shape against the load combination, service load combination, apply. So now it's exceeding the allowable limits, 28 millimeter. That will be more than 25 millimeter. Second check. So show soil pressure. Okay, against service load combination. Okay. So now the soil pressure is also exceeding the 200 kilopascal So it means our bearing check and settlement check is failing. So now I will provide the strap foundation and try to save or try to pass these both checks by providing the beam of strap foundation. Okay, so here you will click draw beam element. From here you will select your beam. You can define more beams, but I have defined only one beam that will be 300 millimeter by 600 millimeter. I will click center point of one footing and take to the other footing center and press escape. Okay, now you can see in the 3D extrude view, here is a 3D. So here that's how the strap footing will be look like. Okay, you can also exceed this beam further to the end, but if for the designing of strap foundation, that will be okay if you move from the center to center. Okay, so now I have defined the beam. Now I will again run analysis and design. Okay, software has successfully done the analysis and design. Now I will check display, show deform shape against load combination, service load combination, apply. Let's see what are the deformation. Now the deformation is less than 25 millimeter. It means our deformation check is okay. Now check the show soil pressure against the service load combination, apply. Okay, so our soil pressure check is also okay, that is less than 200 kPa, so it's also going to okay. So we have successfully modeled the strap foundation. Now for the designing of footing reinforcement and beam reinforcement, the method of detailing is almost same as we have did in the previous lectures. So for the checking the results, before that we have to define the strip. Here I will manually draw the strips, draw design strips. For the x direction, if I draw the strip here, then the distance from the strip to the up and to the down means left and right of the strips. So here at the start and end of the strip. So here for example our footing width is 1.5 meter. So for both sides that will be 0.75 meter, 0.75 meter, which will make 1.5 meter. Okay, now I will just zoom the footing and click the start point and okay, that's the one strip. Or in the x direction, for the y direction, same way. Okay, now I have defined the strips. Now I will run analysis and design. Okay, display, show strip forces. Here now I will see the strip forces, for example against the ultimate load combination, for example moment, apply. For example only in layer A, apply. Here strip forces show only in the slabs, mat, foundation, footings, etc. So here in the x, for in the x direction layer A, for layer B in the y direction. Here is the moment value. Similarly for shear values. Wherever we define the strips, the software will give us the results. So here I have defined the two strips. Okay, now for the forces in the beam, in the strap beam, show beam forces. Okay, now for the, for example major moment, for example load combination, here we can see the moment values. Similarly the major shear value, Here is the major shear value. Okay, now if we want to see the beam design, and for example, first of all we see show beam design. Okay, longitudinal rebar reinforcement apply. Here software will tell us how much top and bottom reinforcement is required. Okay, for example, if we impose the minimum criteria. Okay, now that's how we can see the strap foundation reinforcement details. For the slab detail, that is the same way as we did in the previous lectures. For example, apply, none, apply. That is basically previously click this method. Basically that is providing for the how much spacing is required in the x and y direction. For example, here that is for example 12 millimeter bar at 200 millimeter spacing top, and for bottom 12 millimeter bar at the rate of 200 millimeter center to center apply. That is satisfying. For example, if we provide the 10 millimeter dia bar apply, so it is not satisfying. So for example, either we have to reduce the spacing or increase the dia of bar. So it is up to you. You can play with that. Apply. So that's how you can analyze and design the strap foundation in CSI SAFE software. So that's all. Have a nice day. In this lecture, I will show you how to analyze and design the pile cap footing in CSI SAFE software. Here is the data for the input for the footing pile cap design. For example, the input data of the column that is coming from the with taking the load from the above stories to the foundation. So here is the column width 0.6 meter by 0.6 meter. Here is the FPS unit system. Software automatically calculate the values in inch and KSI in kips, and in system the metric data. So here is a material rebar material property rebar, that is reinforcement for 20 megapascal and concrete is 24 megapascal. Here is a modulus of elasticity of steel bars, that is a 200 megapascal, meaning 200 GPa gigapascal. Modulus of elasticity of concrete, that is a 23,000 megapascal. That is calculated by using ACI formula. Here is if you want to calculate the modulus of elasticity of concrete in SI units, that the formula is 4700 under root FC prime. Here the formula is applied 4700 under root FC prime. FC prime is E11 is 24 megapascal. The software automatically calculated the modulus of elasticity of concrete. Here is the pile data that is coming from the geotechnical report or pile analysis. Here is a pile diameter, that is a 0.6 meter. Safe load of pile means this pile of diameter this and length of this can carry the safe load of 800 kilonewton. So here is the pile analysis software. Here you can put the details of your geotechnical report, means see phi data. Okay, pile, it's a circular pile or square pile. For example, circular pile, diameter, length, and safety factors. Here software calculate the capacity. Here software will calculate the capacity of this pile, and at the end results. Here is the results, means the allowable load can be applied on the on this pile here. So all these things coming from the geotechnical analysis. This data means pile diameter, safe load capacity of a single pile, and length of pile. Then the loading data, which is coming from the above stories to the from the column to the foundation. Here is the axial load, that is a 7130 kilonewton, and mx and my is the moments kilonewton meter. And here is a spring constant. Spring constant is calculated for the modeling of the pile cap in the CSI software. Here is the area of cross section of pile in meter square. pi by 4 into d square, that is a 0.33, and here is a spring constant EA over L. Okay, here for example this is a length of the pile and K is a EA over L. This is the basic formula of modulus of elasticity, stress over strain. Here you can see again, and delta you can take on the left side, means F over delta is equal to K, or EA over L is equal to K. So for the calculation of spring constant for the piles, here is the formula EA over L. Here E is the modulus of elasticity of concrete. Here when I click length, modulus of elasticity of concrete, and area of cross section of pile, the software will calculate the spring constant for the piles. Now how many piles are required? For example, this is the safe capacity of one pile and the applied load is this axial load and moments. Here is a calculation formula. Okay, here calculate number of piles. It's the formula is equal to 1.15 multiplied by axial load, that is a 7130 kilonewton, and the allowable capacity of one pile, that is 800, multiplied by 1 plus ex into 1 plus ey. Here is ex is my over p and ey is mx over p. And 1.15 is the safety factor for the calculation of number of piles. Here the required number of piles is 10.4. So the number of total piles rounding upward, that is 11, but due to the symmetric geometry, symmetry of geometry, for example I will provide 4, 6, 8, 9 piles. Here is a 12, means 4 rows in the x 3 rows in the x direction, 4 columns in the y direction. So for example, so here in this data, the software is calculating the 12 number of piles automatically. You can, if you put the number of piles, software automatically calculates its spacing of pile, edge distance, all the data. For example, here if I'm changing it to 11 or 12, there is not changing much in the piles. So here you can see the for example number of rows, or you can take it as 11. For example, the number of rows in the x direction 3, 1, 2, 3, and the number of pile on each row will be 4, 1, 2, 3, 4. Okay, and number of column in the y direction 4, 1, 2, 3, 4. Number of piles in each column will be 3, 1, 2, 3. So means 12 piles will be needed. Spacing between piles in x direction, in y direction, here is the that is a 1.95 meter. So how we will calculate the spacing? Here is the formula. Minimum spacing between the piles, that is a 3 times of dia of pile, that will be for friction pile. For end bearing piles, that will be 2.5, similarly 2D, and maximum spacing that can be 60. So here all the data of the D. And for the edge spacing, for the edge piles, so here that can be from D to 1.5D. So for S minimum I have taken the 3D spacing. For spacing I have selected the 3D, and for the edge spacing simple D. So here spacing between piles, that is a 3 times dia of pile. Here you can select, here is the dia of piles, 3 times dia of piles. Here the spacing is a 1D. I have selected for the edge of the pile. The total length of the footing in the x direction, that will be 7.15, and total width will be 5.2 meter in the x direction. In the y direction, that will be footing, pile cap length and width. Okay, so here you can also see calculate the total length. For example, these are the spacing and the edge distances. 2s plus 2e will be length, and width of the pile cap will be S plus 2E. Software automatically calculate in this for the length and the width of the pile cap arrangement. There are different types of pile arrangements also, for 1 pile, 2 pile, 3 pile, 4, 5, 7, 8 number of piles. You can change the arrangements as per your requirement. But for this example, I am taking the symmetrical, means 12 piles, uh, 3 rows in the x direction, 4 columns in the y direction. Okay. So I will take all the data and design the pile cap in the CSI SAFE Foundation. Here I am selecting define new model. Here I have selected ACI design code 31814 units, that is currently metric. Okay, you can change it to US defaults, mean FPS system, metric, consistent units, but I am working in this example in the kilonewton meter, so I have selected OK. Now I will select the grid only. Here I will provide the grids, that is 2 in the x direction, 2 in the y direction. Here is the x direction spacing, you can select from that is the 7.15 meter, that is the x direction length of the pile cap, and the width is 5.2, that is 7.15, that is 5.2 meter. Okay, you can more deeply edit the grid data in this more detailed grid data. Okay, so when I have selected OK, the grid system have been drawn. Okay, 7.15 and 5.2 meter is the width of the pile cap. So here first of all I will define the material property. I will define a new material. For example, I am defining concrete 24 megapascal. Here I will select concrete material. Here is a density of the concrete that will remain same. Specified concrete strength, that will be 24 megapascal. 1 Newton per millimeter square is equal to 1 megapascal. Okay, modulus of elasticity, I will put the formula equal to 4700 multiply by square root of 24 power 0.5, means square root of 24. I will click enter. Software automatically calculate the modulus of elasticity of concrete. Okay, Poisson's ratio of the concrete, that will be 0.2. Thermal coefficient, that will be also constant. Shear modulus, software automatically calculate. Okay, that's how you can define the concrete property in CSI SAFE. Here I will define the material property for rebar, means for reinforcement, that will be Fy for 20 megapascal. Here I will select the material type of rebar. Okay, weight density of the steel will also be remain same. Here modulus of elasticity, that is 199 GPa. I will put it to 200,000 GPa. Yield strength of 420 megapascal steel, that will be 420, and the ultimate strength will be 630 or 620, either it's okay. Okay, now I will define the section properties for the pile cap and piles. Define slab properties, add new property. Here I will define the pile cap. Okay, thickness, here I am defining the trial size, that is 800 millimeter. Here I have selected the concrete 24 megapascal. Here I will select the mat for the footing, because it is facing the interaction as the mat foundation, 800 millimeter. Okay, now I will define the material for the pile. Here for example, for pile lengths, you can take the data. For example, the piles are of 14 meter, you can put the 1400 millimeter thickness. So it will not matter, because we will define the spring constant which will cover the length of the pile. So here I will just define 800 millimeter pile. 800 millimeter for pile. I will again select the mat. Okay, now for the data of the column, I will add new property, column. Okay, concrete 24 megapascal. Here I will select for the columns stiff member, because columns are our stiff members. Okay, here I will again select the 800 millimeter. Okay, column have been defined. Okay, now for the geometry, that is a 7.15 meter. I have to draw the geometry for the drawing of piles. The edge spacing of the pile is 0.65 meter. Here I will draw. Here is the draw points. Here I will draw 0.65 by 0.65. I am drawing by my method. You can use your method by using your thinking. Here I have drawn first point. Now the spacing between the piles is 1.95 meter. 1.95 meter. The y offset, for example, I'm putting 0. Here I will draw the spacing between piles. Here I have drawn in the x direction. Similarly, I will draw the grid points for the piles in the y direction. 1 2 3 4 1 2 3 4. Okay, the data for all the piles have been drawn, and for the column location at the center, here I will put 0. Here I will put equals 1 2. So that is the center of the spacing of the piles, half distance. So here I will click OK. So that's the center location of the pile cap where the column will be drawn. Okay, so now I will draw one by one things. Here for example I will draw for example, first of all I am drawing the pile cap. Here is a pile cap of 800 millimeter. Here is the first point. Click the end point. Here is the pile cap slab. Okay, now I will draw the, for example, pile caps, simple piles. For drawing of piles, I will click quick draw area points. Okay, here I will select circular slab. Okay, here I will select the pile. Here I will put the diameter of the pile, that will be 0.65 meter. Okay, I will go one by one at each point. Okay, all the piles have been drawn. Now I will again go to rectangular slab and select the column, that is our stiff member. Its dimension will be 0.6 by 0.6. Okay, meter. I will click at the center. The column will also be drawn at the center. Now I will click the center point of all the piles. 1 2 3 4 5 6 7 8 9 10 11 12, means 12 points have been selected. Now I will go assign load data, click spot data, click point springs. Here already a spring have been defined. I will click add new property, a define new spring, that will be pile spring constant. Okay, here is the unit system of the for the data is in kilonewton millimeter. I will cancel, go in the units and click consistent units and select I will select kilonewton meter. Okay, then I will go you can select again by clicking one by one, or just go select get previous selection. All the 12 points one point is not selected yet. Here, select here. Okay, now I will go assign sport data point springs. Okay, add new property, pile spring. Okay, now the units in kilonewton per meter. Select here the compression only for the foundations. Here is the spring value, that is a 545 sorry, 545 748 748 748. Okay, kilonewton per meter. Okay, okay, now you can see the pile springs have been defined under each pile. Okay, now again click in the plan. Now select the center point of the column, go to assign. For the assigning of load data point loads, here you will apply the loadings. Here the loadings are 7130 axial, and these are moments 85 and 330. 7130. Here in the gravity direction means downward direction 0130, that is the axial load. Mx is 85, My is 330 kilonewton. Okay. Okay. Then for the calculation of punching shear around the column, you have to put the dimension of the column 6, that is a meter, so you have to put 0.6 meter. Okay, and press OK. We are considering all the loads coming from the above and in the dead, and also taking the self weight of the footing. Okay. Okay, how the software will take the self weight of the footing? Here is a self weight multiplier. In the case of that is 1. Software automatically take the self weight of the footing. Okay. Now I have defined the piles data, pile geometry, loads coming from the above. All the you can see in 3D here. Three loads have been applied: axial, 2 moments. Okay, for moments there are 2 arrows, that is the moment showing notation, and for the axial load only 1 arrow. Now I am going XY. Now I will check one by one. Click run analysis and design. Before running analysis and design, I will recommend please go into run, and here automatic slab mesh option. Here you can select 1 meter, 0.5 meter for getting more accuracy. For appropriate results, 1 meter size of mesh is okay. Now I will click run analysis and design. Okay, before running analysis and design, software is saying pile cap. For example, this one is example 2. After saving the model, software automatically start analysis and design of the pile cap. Okay, here is a default deformation shape of displacement against that is appearing. Now I am going display. For example, let's first see the show punching shear design. Here the value against each footing, the values coming for the punching shear, all the values are less than 1, but at the center of the column that value is 2, means punching shear against the column loads is failing. Okay, we have to increase the thickness of this pile cap foundation. Okay, let's see the second, the reaction forces against dead load point reactions. You can select all, apply, close, see in 3D. Okay, let's see the reaction in this, that is a 262 kilonewton. Here in this, that is a 1197, which is exceeding the allowable capacity of one pile. Allowable capacity of one pile is 800 kilonewton. In these two piles the load is more. Okay, again in this pile means that is the failing. So now we have to increase the thickness of the pile. Here I am unchecking the model. Okay, now I'm going to define slab property. I am increasing the thickness of each material. For example, here for column I'm putting 1 meter, for pile also 1, for pile cap that is a 1 meter. Okay, the headings are same. You can also change the headings, but software automatically consider these upper values. Now I have defined the higher values. Okay, now I will again run analysis and design. Okay, okay, now analysis and design have been enough. Show reaction. First check punching shear design. Here now the value is reduced from 2 to 1.4, and in all the remaining piles the punching shear is okay. Let's see the second value. Show reaction forces. Apply. Okay, in 3D. Here the value is also reduced to 1034, and here the value is reduced to 1005. Okay, now I am here is 800, 442. Okay, the values are changing. So now I am increasing the thickness of this pile cap to more higher values. For example, I am going into define slab section. For example, I am taking the thickness is to 1.5 meter, means 1500 millimeter. Okay, change all the values. 1.5, 1.5. Okay, now again run analysis and design. Now go to display, show punching shear design, go into XY plane. Okay, now punching shear design, all the values are less than 1, so it means punching shear design is okay. Now I will check the reaction. Show reaction forces. Apply. Okay, in 3D let's see the reaction forces in each. Here the values in these two piles. In these two piles the reaction forces which is coming downward is still a little bit high, that is a 826 and that is a 859. Similarly, you can increase the thickness of the pile cap, and or you can increase the capacity of the pile by increasing the dia of pile. So these are the parameters you can you can increase the capacity of the pile cap foundation. Okay, so here similarly you can go upward. So now I want to show you how you can see the reinforcement in the pile cap. So here I will go display, show slab design. Okay, here I have not defined the strips, so that's why software is not showing the layer A and layer B. I will go again back, go edit, add design strip data, 1 times in the X direction and 1 times in the Y direction. Name is B. Okay, strips have been defined. Only at this location and this location strips have been defined. You can draw manual. For example, here draw design strip. For example, A, that is in X direction. For example, here I am picking the point and drawing the if these points are not snapping, you can, for example, I have press escape. Here the point have been defined. First of all, I can draw the points, okay, so that I will not face issue. For example, the edge spacing is 0.65 meter. Here I will draw points minus 0.65. okay, here, similarly in the positive direction. Okay, in the y direction 0.65 meter, here, here, here. In the negative direction I am putting minus. Okay, now I can easily draw the design strips. In the x direction, design strips are A. Here is the start point, end point. Second, that is drawn automatically by the software here. Okay, now for the in the y direction, that are B. Okay, now I will again run analysis and design. Okay, now you can also see more detailed things. I have checked the punching shear design direction. Here you can check the short strip forces. For example, I want to check the movement. Apply. Here software will show the movements at the location of strips where I have defined. In the x, these are A, they are A in the x direction strips, and for the B in the y direction strips here. Okay, the data of movements. For example, here the maximum moment is coming 25 or 2600 kilonewton meter. Okay, now I will go in the display for the reinforcement design, show slab design. Here now these both options are appearing. A and B are enabled, or you can check in the previous these are not enabled because I have not defined the strips. Now I will click apply. For example, for layer A only, here you when the move around the strip you can see the top and bottom reinforcement requirement that is showing in the millimeter scale per meter. Okay, in the meter scale per meter that is too small. Here I will select metric. Okay, now you can see in more better way millimeter scale per meter. Here at the edges 1800 millimeter square per year, here 3500 3600 millimeter square. Similarly, show slab design in the layer B, here in the y direction, top and bottom. Okay, so for example I am providing both, so you can also decide what bars are enough for this foundation. Here I am providing the typical uniform reinforcement. For example, I am selecting 20 bar dia at the spacing of, for example, 150 millimeter. Similarly, 20 bar dia top and bottom reinforcement 150 millimeter. Apply. So here the extra bars are needed. Okay, for example, I am reducing using 25 millimeter dia bar. Apply. Okay, still at these locations uh, apply. Okay, so if we provide 25 number 25 bar at the spacing of 100 millimeter, so in the top and both directions, then the design then this reinforcement will be enough for the designing of the pile cap, which will cover the or which will act as a capacity of this pile cap to resist the applied loads. So that's all. You can analyze and design the pile cap in the CSI SAFE Foundation. In this lecture, I will show you how to analyze and design the cantilever slab. So start from File, New Model. Here the design code, design preferences. For example, which code you want to use, which design parameters, means factors for the design. Okay, and project information, you can put any information. Here the units, you can use FPS system, metric system, consistent, up to, for example, in Newton millimeter, kg meter, any unit system. Okay, or you can also either change here unit system. Here I am selecting metric. Okay. Okay, now I am clicking grid only. Here I am selecting the grid, for example, true grid in x direction, true grid in y. The spacing between the grid, for example, 3 meter in x, and the y direction is also 3, or you can put 3.5 meter here. For detail editing, you can click edit grid. So here I am hitting OK. The software have drawn the grid. Now I will draw this slab. Before material property, I will use as it is for steel and concrete material property. I will define the slab section, add new property. Here I will define the slab 150 millimeter thick, that is 6-inch slab. The concrete material already defined, I am not defining in this lecture. Here the slab property. Here I will click 150 millimeter. If your slab have different thicknesses in different directions, you can click in to orthotropic. Otherwise, this 150 millimeter and thick plate is okay. Okay, and hit here. Okay, I have defined the slab. Now I will draw the slab. Here I have clicked the rectangular slab. Slab property 150 millimeter, which is I have defined. I will click from here to here. Okay. Now I want to make this rest of the portion cantilever, and this I want to make this edge as a support for the cantilever slab. So I will click here. I will click just one edge of the slab. Here you can see one area, one edge selected. This left edge has been selected. I will go in the assign support data. Before going in the support data, I have clicked this area of the left side. I will go edit areas, divide area. Okay, or you can click split area edges. Okay, now I want to make this edge to divide into different points. Here I am selecting, for example, for this 3.5 meter height. So for every for example, here I am selecting, for example, 35 points. Okay, now software had drawn 35 points on this left edge of the slab. I will click all the points and go to assign support data, click point restraints. Here you will select fixed support. Okay, now this left edge of the slab is supported and the rest of the slab is will remain as a cantilever portion. So now I will select the slab and go to assign for the loading condition. Here I will click surface load. Here I will define, for example, live load of replace existing. Already there is no load, so if any load is present, software will replace the existing load. Here for the live load, for example, I am applying, for example, 220 kg per meter square, so that will be 2 kilonewton roughly. If you convert into kg into kilonewton per meter square, you can either change the units, but here I will directly put, for example, 2.5 kilonewton per meter square. Okay, here on all the slab the load have been assigned. Now I will save the model. Okay, here I will save the model with name cantilever slab. Okay, now model have been saved. Now I will go into the run and click on automatic slab mesh options. Here I have to divide this slab portion into small portions for the finite element analysis. Now I am clicking, for example, 0.5 meter. Okay, when I run the analysis, software make it 0.5 meter by 0.5 meter box of this slab. Now I will run analysis and design. Okay. Okay, now you can see due to the fixed support at this left edge the deformation is 0, but as you move towards the right the deformation is more. Okay, so it means we have successfully modeled the cantilevered slab. So for example, if you want to see the movements, for example display show slab forces here. For example, if you want to see against the load combination of 1.2 dead plus 1.6 live, for example, if you want to see the movement, apply here. At this port, the movement is minus 7.4667 kilonewton meter per meter. So as you move right, the movement is going to less. Okay. So here for the detail moment diagrams, you have to make the strips, design strips. Okay, here I will go edit, add design strips. The software only draw the add design strips on these edges. Okay, on the grids. So I will draw manually, draw design grids. For example, in this direction. For example, first of all, at this port here, here. Okay, now for the middle strips. Okay, you can make as much as many you required. You can draw many design strips. Why I have drawn, I want to see the movement at this section. For example, I am running this analysis and design. Now I will go display, show strip forces. In the strip forces against the combination, there is one combination 1.4 dead according to ACI, 1.2 dead plus 1.6 live in this combination. I will show it in this combination what load parameters are there. First of all, I want to see this against this combination. Apply here. You can clearly see the movement diagrams here. At this port the movement diagram is, now this is not per unit meter, this is the full value kilonewton kilonewton meter, not the per meter. So here at this port the maximum movement is 1,111 kilonewton meter, and it is reducing towards the free end. Okay, so let's see in the define load combinations. Here is two combinations, modify 1.4 dead, sorry, again the same is selected here, 1.2 dead plus 1.6 live. If you do not define, software automatically generate the load combinations. You can also create by yourself. Okay, now I will show the design. For the design you have to again go display, show slab design. Okay, for example here it's there are two different methods for design. There is strip base and finite element. In this lecture I will show with finite element based. Okay, for example in the one direction, this is x direction is one direction, top rebar, how many top rebars are required, apply here. You can see 836 millimeter square per meter here, and it is reducing to the right side. It's a top. Now bottom in this direction, apply. Okay, you can see no steel is required because tension is now on the upward side and reinforcement will be required on the upward side, not the bottom side. So that's the results are too much good. Apply here. In this direction, in the y direction, there is also movement area of steel required. Okay, for example in the bottom again, but at the free edge you have to provide the reinforcement at the bottom edge. So you can also check how many reinforcement is required. For example in the top rebar, apply. So here I am selecting typical uniform reinforcement. For example, if I provide a half-inch dia bar at top at 250 millimeter spacing, is it okay? Not. So I am reducing, for example, 150 millimeter at the top, apply, so it's okay. If I provide the half-inch dia, means 14 millimeter bar area at the spacing of 150 millimeter, that will be okay. So let's see for the bottom, that is also okay. But make sure that you have emphasized the minimum criteria. Impose minimum, apply. So in the minimum there is some steel is required. I am again making it to for example apply. So minimum criteria is okay. So again checking the top rebar, apply, again okay. For this in the y direction is also okay, apply. For this direction is also okay. So if you spacing provide in these in the x and y direction at this top and bottom, your design will be okay. So that's all for the cantilever slab. You can also see the detailing that is I have shown in the previous videos. So that's all. Have a nice day.
In this lecture, I will discuss how to calculate the short-term and long-term deflection in CSI SAFE software. So here is the short-term and long-term deflections. There are basically three main types of deflections are used in the slab analysis. First one is the elastic deflection, means uncracked section, and second is the immediate crack deflection, means with the crack section, and long-term deflection while considering creep and shrinkage. Okay, for example, first of all, for elastic deflection and for immediate deflection, okay, means with uncracked section and with a cracked section. So how? Here are three load patterns I have defined: dead, live, super dead. Okay, here I will define load combination. Okay, add new load combination. I will click live 1, dead 1, super dead 1. Okay, and I am naming this combination as elastic combination. Sorry, elastic combination. Okay, now I will define the load combination for immediate, a load case. Okay, add new load case, immediate all loads. Okay, means with a cracked section. Here I will use one dead, one live, and one super dead. Okay, and in this load case, software will use the crack section. Okay. Before running the analysis, here you will see the crack analysis options. Here you can either put your requirements of these labs as you calculated by yourself and calculate the deflections. Okay, or a software will take the itself from the finite element base design. Okay, similarly user specified rebar objects, and third one here is the minimum reinforcement ratio used for crack analysis. Take it as it is. Okay, for that is will be 420 grade steel. Okay, so now I will run analysis and design. Okay, now the analysis is complete. Now first of all I will see the elastic deflection. Here show deform shape. Okay, I will go in the combination. Elastic combination means uncracked section. Okay, apply. Okay, so here you can see the maximum deflection is 7.5 millimeter in the uncracked section. So here I will write 7.5 millimeter maximum deflection in the slab. So now for the cracked section, apply. Here is a maximum deflection is 16.6 millimeter. Okay, millimeter. Now the third one, how you will calculate the long-term deflection. For the calculation of long-term deflection, we will consider the creep and shrinkage also. And the load combination for the sustained load mean for long-term deflection, that is the 1 dead, 0.25 live and 1 super dead. But when we consider this combination of 25% of live load, then we may ignore the 75% of deflection due to live load, so which is not sustained. So how to accommodate that 75% in the deflection calculations? Basically, we have to take the 100% live load in the deflection calculation, but the load combination for the sustained loads is 25% only. So how to accommodate the 75%? Here is the combination. Here is the long-term deflection basic combination: 1 dead, 25% live, 1 super dead. So here is the subtraction. Okay, how we will consider the 75% of live load without creep and shrinkage. So here we will define another two combinations, one with 1 dead, 1 live, 1 super dead, another with 1 dead, 25% live, 1 super dead. So after subtracting, we will get only 75% of live load, which will not include the creep and shrinkage. So how I will use this combination for the long-term deflection calculation. Here I will click close, uncheck model. I will go again, define load cases. Okay, here I have already defined for immediate all loads. Okay, I will create a copy. Okay, here I will put immediate sustained. Okay, here I will put 0.25. okay, remember I have put immediate sustained means with 25. Here I have used this combination, new combination I have defined, immediate with 25%. okay, and here I have clicked create. Okay, now I will define add new load combination. Okay, I will call it long term sustained. Okay, so here I will define the basic. Okay, here I will put 0.25. okay, and here I will select for long-term sustained non-linear long-term crack section. Here I will consider the creep coefficient and shrinkage strain, that is the default value for the concrete, so take it as it is. Okay, for the long-term deflection. Okay, now I will define the load combination for the long-term deflection. Okay, here I will click long-term deflection. Okay, here I will put long-term sustained as it is 1. Okay, then I will put immediate all loads mean 1 dead, 1 super dead, 1 live. Okay, here I will pick immediate sustain. Okay, here I will put -1. Okay, means now 100 minus 25 will be 75%. Okay, 25% live load is already in this combination, and remaining 75% without creep and shrinkage will be in this combination, 1 minus 1. Okay, so here you can see also. So that's how we define the long-term combination, deflection combination in CSI SAFE software. Okay, now again I will run analysis. Okay, it will take some time because this software is doing iterations. Okay, now the analysis is complete. Now I will go in the display, show deform shape, load combination. Here I will click long-term deflection combination, apply, close. So here is a maximum deflection, that is a 30 millimeter. Okay, so that's how we calculate the deflection in long term and short term in CSI SAFE software. So here is the allowable deflections. If you are calculating the immediate deflection, okay, so the criteria is span by 360. For example, I am taking the longest span, that is here, that is a 7.5 meter. So here is the calculator, 7.5 multiplied by 1000. I will divide it by 360. Okay, the allowable deflection is 20.83 millimeter. Okay, in the immediate, that is less than 20.8 millimeter. So our deflection at the immediate, that is okay. So let's see for the long-term deflection. Here again, display, show deform shape, apply, okay. Okay, that is 30.16. So for 7500, okay, divided by 250, okay, the allowable deflection is 30 millimeters. So that is nearable to the deflection due to applied loads. So even you have to also check that this maximum deflection is in which panel. Okay, so here in this panel, that is not 30 millimeter, so that will not govern in this segment. So in this not, so here you can see in this segment we have to increase the stiffness of the section, either by providing camber or by providing beam elements with stiff sections. So that's how we can compensate the deflections in CSI SAFE software. So that's all. Have a nice day. Hi, in this lecture I will discuss about modulus of subgrade reaction, okay, that is used for the design of foundations. So what is modulus of subgrade reaction? Modulus of subgrade reaction is used as primary input for rigid pavement design. It estimates the spot of the layers below a rigid pavement surface course, means under the foundation there is soils, means a layer of soils. So for the simulation of that layer of soil in the softwares, we use the modulus of subgrade reaction. The K value can be determined by field tests or by correlations with other tests. There is no direct laboratory approach or procedure for determining K values. Okay, so for the design of foundations, we have to use some method or some researcher guidelines. So how we use the modulus of subgrade reactions. There are different approaches given by different authors. For example, basic approach method that is given by Westergaard, Wizik approach, okay, Terzaghi approach, Bowles approach. There are different approaches for the modulus of subgrade reaction. So in this lecture, I will discuss only two that is really used in the field. So one is basic approach method. The second one is the Joseph E. Bowles approach method. Okay, so first one is what is the modulus of subgrade reaction. So all will be covered in the basic approach method. The modulus of subgrade reaction came about. Why this came about? Because work done by Westergaard during the 1920s developed the K value as a spring constant to model the spot beneath the slab. So it behaves just like the spring. So the modulus of subgrade reaction, it behaves like the spring. For example, you apply the load, the deformation will come under. So that all depend the stiffness of the springs. Okay. So here the reactive, for example, here the figure 1 shows. In the figure 2, the reactive pressure to resist the load is thus proportional to the spring deflection. Means the pressure, the load which you applied is directly proportional to the deflection. So here is the K spring constant. Here is the numerical expression P is equal to K delta, where P is the allowable pressure and delta is the allowable deformation. So that is the approach I have used in my previous lectures. So here is the approach which is I have used in my previous lectures, that is K is equal to pressure over deformation. Okay, so here is the formula for modulus of subgrade pressure over settlement. So allowable settlement is 25 millimeter. So I have converted into meter, 25 divided by 1000. So result is 8000 kilonewton per meter cube. So that's how I have calculated the modulus of subgrade reaction in my previous lectures. So let's see. Here is the modulus of subgrade reactions in the book, that is Foundation Analysis and Design, 5th edition by Joseph E. Bowles. So that is the basic approach, that is allowable pressure divided by allowable settlement. Okay, so there are different approaches for the calculation of modulus of subgrade reaction. Plate load test. Okay, so here is the Terzaghi approach, that is the formula. Here is a Wizik approach. So here at the end, Bowles provided its own approach, that is the Bowles approach, okay, for the calculation of stiffness modulus. Okay, so how Bowles calculated the modulus of subgrade reaction. So here, so let's complete the sentence. The modulus of subgrade reaction is estimated from other strength/stiffness tests. However, in situ values of value of subgrade reaction we can also find in the field by using plate bearing test or plate load test. So now comes the second approach for the modulus of subgrade reaction. So here Bowles recommended following approximation to determine Ks, means modulus of subgrade reaction, based on allowable bearing capacity as suggested by geotechnical engineer. Okay, SI means System International Metric System. The modulus of subgrade reaction formula is Ks is equal to 40 into factor of safety factor multiplied by QA, allowable bearing pressure. In FPS, that is 12 into safety factor multiplied by QA. So here, so how the Bowles calculated this? SI is equal to 40 into SF. The Bowles uses only the difference is Bowles uses the ultimate bearing capacity instead of directly allowable in the formula. For example, here I have used allowable pressure divided by allowable settlement, but Bowles used here Bowles used the allowable bearing ultimate bearing pressure. So here for the calculation of allowable bearing pressure we calculate by using Q ultimate, that we calculate from formulas like Terzaghi, Wizik or Meyerhof. Okay, Q ultimate divided by safety factor, that is Q allowable. So for the Q ultimate you will multiply with the safety factor, you will get Q ultimate again. So Bowles use that value. So again, modulus of subgrade reaction, Q ultimate divided by delta H. That's the approach of Bowles. Bowles not using the Q allowable in the upper portion. So what happened next? Okay, here is the Ks, Q ultimate divided by delta H. So the ultimate soil pressure is considered at the settlement of 25.4 millimeter, or you can round about it to 25 millimeter, that is 1 inch. So Q ultimate divided by 1 inch settlement or 25 millimeter settlement. So when you divide that value, and now I am again writing in the form of QA into safety factor. Okay, so when you will 1 divided by this, then the calculator will give you the value of 40. 1 over 0.0254 equal to 40. So 40 SF into QA. Q ultimate is equal to QA into safety factor. Bowles uses Q ultimate because Bowles suggested that we are using the modulus of subgrid reaction for the simulation purpose. So for that purpose, we should use the Q ultimate not as the safety factor. So that's why safety factor is multiplying, not in the division sense. So 40 into safety factor into QA. Okay. Similarly, in the FPS system, one in settlement, same formula. Okay. And we will get the 12 SF into QA, where delta H means the undervalue delta H is considered 6, 12, 20 millimeter and so on. In this example, we have used 25 millimeter. The 40 factor will come upon using 25 millimeter settlement, but 40 is the considerable sufficient conservative value, but one can choose smaller displacement value depending upon their needs. Okay, so now let's see an example with both methods, with basic approach and with the Bowles approach. So here is the input data for the problem. Here is the footing with 2 meter by 2 meter, mean X direction and Y direction. Footing thickness is 600 millimeter, and column size means column size is also 600 by 600 millimeter in scale. The dead load is 1000 kilonewton and live load is 1000 kilonewton. Okay, so I have already modeled the example with soil subgrid modulus with the basic approach and with the Bowles approach. So now I will just close it. Okay, so here is the example, same example, 2 meter by 2 meter, right click, you can check the loads, 1000 and 500 kilonewton. Okay, so let's see the modulus of subgrid reaction, soil subgrid modulus. Okay, here is the value, basically 2000 kilonewton per meter cube. Here I will put the value of modulus of subgrid reaction. For example, I am assuming the allowable bedding pressure, that is 100 kPa, and the factor used for the allowable bedding pressure, that is 2.5. It is vary between 2 to 3. So which factor we use, it depends upon the soil type. So let's suppose we calculated the allowable bedding pressure after applying the safety factor 2.5. So allowable bedding pressure is 100. Okay, I am dividing with 25 millimeter. You can round it or you can use 25.4 millimeter. Okay, I will just hit enter. So I got the modulus of subgrid reaction 4000 kilonewton per meter cube. Okay, for that is for the basic approach or the Westergaard approach. Okay, so now you can click footing and soil, assign in the soil 4000 modulus of subgrid reaction is assigned. Okay, the same example but with different modulus of subgrid reaction based on Bowles approach. Okay, Bowles approach, define soil subgrid modulus. Here I will use 40 into safety factor, that is 2.5, into allowable bedding pressure. Okay, that is 100. So now I am getting the modulus of subgrid reaction 10,000 kilonewton per meter cube. Okay, now I will run both examples. Let's see first example by basic approach. Okay, so let's see the punching shear value. Here show the punching shear value, so 0.4721. So let's see the first run the analysis and design and go display show punching shear design. Okay, the value is nearable, not much difference. Okay, with the change of subgrid modulus. So where the difference will come, that will come in the deformation, we will see at the end. So now see the soil soil pressure values. Okay, so here soil pressure, apply. In the second combination, close. The soil pressure is 106 and 109. So let's see in the Bowles subgrid modulus approach. Okay, soil pressure, not the point direction, soil pressure against normal combination, service load combination 2, in which 1 dead plus 1 live is used. Live. Okay. So let's see the values. That is 106. Here is 105, 109, and 111. So not much big difference in the even in the pressures. So where the difference will come by using the different Bowles approach, modulus of subgrid reaction, or basic approach. Here see display, show deformed shape. Okay, in the load combination, we will see against the normal combination 2, apply. So here the deformation comes, maximum deformation is 27 millimeter in the negative. Display, show deformed shape, load combination, apply. Okay, let's see. Here the deformation is 10 or 11 millimeter. So much difference. Why? We use the higher stiffness modulus, or modulus of subgrid reaction is small. Okay, so what's the difference? We will need the smaller thickness foundation in the modulus of subgrid reaction by Bowles approach. That is also used in the field for many years. People are also using this approach, that is approximate approach, but giving the good result. Okay, so in the conclusion, the both approaches are working in the design field. Bowles approach of modulus of subgrade gives conservative and satisfactory values for the design, depending based on experience from the previous values. It giving the good values. But the basic approach is too conservative and based upon the basic phenomena. Okay, basic design philosophy. Okay, it is extreme safe side and it follows the basic philosophy of spring constant. So I will recommend to you, you can use Bowles approach, modulus of subgrid reaction, and it is safe, also safe to use in the design. Okay, so you can also use the higher modulus of subgrid reaction based on Bowles approach. So that's all for the foundation for the modulus of subgrid reaction used in the designs. So that's all. Have a nice day.
SAFE is a CSI software which is used for the designing of slabs, beams, foundations like isolated, combined, raft or mat footings. So here in the help we go in the about SAFE. SAFE 2016, what the abbreviation of SAFE? It's a slab analysis by the finite element method. So first of all, I will show you how to define the material properties in the SAFE software. File, new model. First of all, the user can select the code as per his country. So here I am selecting ACI 31814, design preferences, definitely the code, etc. Here is again the code, phi tension, these are the factors for compression, for shear, minimum cover for slab, and what bar I am preferring. So all these settings is present in the design preferences. In the project information, here you can put all the information, and when you go for printing and for reporting, then all the information automatically comes on the report. Then the fourth one is the